The mass of this ball is given. The distance to the center of the mass of the ball from the point of the support is 95 centimeters. The ball is released from rest when the string is horizontal. When the string becomes vertical, the ball collides with the block of mass
Hello.
2.4 kg that is at rest on the horizontal surface. Okay, fine, no problem.
He's been joining the
Just
class.
before the collision of the ball with the
Ball
block,
kari.
draw the free body
Nitte
diagram
jahi
for
ja
the
gaya na.
ball.
Thoda ja nitte
Okay,
nu.
so what is the free
Nitte
body
nu
diagram
bole
for the
pila
ball? First
bole.
of all, we have to see, and what are the forces we have to see.
Dono da jada same
So the
nitte
first
uppa hoga.
force that will be there is obviously the weight, isn't it? So weight will be there. You can't get rid of it. Weight will be there. What else do you think is there? Tension? Yes, the tension in the string is this. Now, the tension in the string is also acting like the centripetal force because of which it is moving in a circular motion. So, because there is no upward and downward force,
Hello.
no, but there will be bigger force here. So, tension will be more than weight. Sorry. So tension will be bigger because it has to cover up not only the weight, but it has to provide the centripetal force also. That is why. So the tension will be bigger, the weight will be smaller. There is another explanation that I can give you here, but that is with respect to centrifugal force, and the IB books are not even talking about it. So, if you want to skip that part, it is your choice, but I would be telling you whenever a body is moving in a circular fashion, there is a force in the downward direction which is equal to centripetal force, but it is in the opposite sense. And that is called the centrifugal force. Centripetal force, like imagining centripetal force, is difficult, so that is why you can get rid of that and you can come to centrifugal instead. So this is centrifugal. Weight will definitely be there. So clearly the tension will be bigger because it will be like addition of these two. Now you can very well get rid of the centrifugal force from the free body diagram. Why? Because neither the centripetal nor the centrifugal is the real force. So T and W are the real force. Some or the other force has to act like centripetal or the centrifugal. So that is why we will not be showing them in the free body diagram. So this is what will be your answer. This will be weight W, and you can have a bigger force there, and that will be the tension T. Anyways, so let us move to next question, and then I will be showing you the mark scheme also, and we will verify this answer also. Show that the speed of ball is about 4.3 meter per second. Okay, let us see. Yeah, so we want to find the velocity of the ball at this point. Obviously, conservation of energy will be the most suitable method that we can apply here. So the potential energy here will be equal to kinetic energy here. We can assume the potential energy here to be zero. We are taking this as the datum. Datum means like the reference point from which the height is measured in regards to potential energy. So the height of this will be equal to, from the center of the ball to this, that will be equal to 95. So height will be equal to 95 centimeter. So the mass of the ball is now 0.8 mgh is equal to half mv square. Or we can directly find this thing like v is equal to root of 2gh if you remember this formula. Okay, we have done this formula in the case of dropping, in the projectile motion and kinematics. So you can just apply this formula directly, because every other thing, like even this formula, is going to be reduced to this only. So anyways, velocity will be approximately, you can take it as 10, but I don't know whether your book, whether the answer will be doing like that or not. Anyways, 95 into 2 divided by 10 square root, that will be the answer. So I don't have the calculator with me presently. We can just assume it to be 100. So that will become 200 and square root of 20. Approximately square root of 20. So 4 is 16, 5 is 25. So it should be approximately equal to 4.5. Yeah, that is what is the answer, 4.3 to be specific. Anyways, so this is all the approximate calculation that I'm just doing it here because I'm not presently having calculator with me anyways, to be honest. But otherwise also the calculation is not required. I will show you this thing in the mark scheme. This is the equation that you have to solve. If you have the calculator, you want to go that way, you can. So this will be the this is how we do, and the velocity for this will be 4.3, and I'm getting approximately 4.5. Determine the tension in the string. So we have to find the tension in the string now. So as I have already told you, just a moment. As I already told you here, that tension will be equal to, like, now this is only and only for you. You're not going to draw this in the IB examination, because IB board does not recognize centrifugal force, so you are not going to draw it. You can draw it in the rough work. So this is the tension, this is the weight, and centrifugal. By the way, centrifugal force is equal to centripetal force. So tension T is equal to W plus the centripetal, and we don't know what the centripetal force is, so we would be just applying the formula mv square by r. Radius is given, mass is given, velocity is 4.3 meter per second. You can find the centripetal force, weight is m into g, and you can find the tension T. Okay, so the tension T will be, what is the mass given? Yeah, here is the information. So tension T is 0.8 into 9.8 plus m v square divided by 95 centimeter. So it is converted into meters by dividing it into 100. So 0.95 meter is the radius. So mg plus mv square by r. So this will be your answer. And how to do this thing now? Let me go to the mark scheme now, because otherwise I'm not having the calculator now. In the next video I will be having. Okay. So no worries. Okay, so these are the answers now. So as you can clearly see here, the weight is shown below and the tension is upward, and clearly the tension is bigger in the magnitude than the weight. So it's exactly what I told you. Now the velocity is root of 2gh they have taken, and the same thing that we did, and so the answer is 4.32. And here you can see tension is equal to mg plus mv square by r, and that is why your answer is 23.5 Newton. So 1A is completed. All the answers have been matched with the mark scheme. So going back to our question now. Yeah, we're going to question 1B now. Yeah, okay, it's so much down there. After the collision, the ball rebounds and the block moves with the speed of 2.1 meter 6 to 2.16 meter per second. Show that the collision is elastic. See, before that, we must understand what are elastic collisions. Collisions are of three types. Number one, elastic. Number two, inelastic. And number three, totally inelastic. So elastic collision is the one in which there is no loss of kinetic energy. So we will show that the total kinetic energy before the collision is equal to total kinetic energy after the collision. Okay. And we're talking about the total system. So we are going to consider both of the bodies every time. So we would be finding the total kinetic energy before collision and after collision. If it comes out to be equal to each other, it is elastic. Otherwise not. Momentum is always conserved. I would be coming to that point. Now point number two is inelastic collision. Now what are inelastic collisions? Momentum is always conserved in a collision, whether elastic or inelastic, but in inelastic collision the initial kinetic energy is not equal to the final kinetic energy, so there is a loss of energy involved here, and that is why we will call it inelastic. Now what is totally inelastic or perfectly inelastic? Now totally inelastic means that maximum loss of kinetic energy is happening. And what is that case? When the two bodies start moving after the collision, they are sticking together. So it's basically the bodies stick together after the collision. That is the condition. So like let's say there was one trolley and the trolley was going, and you have thrown a ball into it, so the ball is now getting into the trolley. So after the event has taken place, the ball and the trolley are moving with the same velocity. That is what is called totally inelastic. Okay, or you are throwing something at some other body which is moving, and the body that you have thrown is just going to stick there. If they are sticking there, we say that this is having maximum loss of kinetic energy. Now the question is about elastic energy. So we want to confirm that whether kinetic energies are equal to each other or not. Let us now see. So according to this, the ball, it was coming, I'm just talking about the moment when it is about to strike, and after the collision is like when it is like just it strike with the block and rebound is taking place. So it is moving with the velocity 4.3 meter per second, but the block is not moving. And after the collision, the ball is rebound. Rebound means that it is moving exactly with the same velocity, but the block is now moving with a velocity of 2.16 meter per second. We will be needing the masses also. So this mass was 0.8 kg. I remember this, but this mass I'm not remembering. Unfortunately, we have to go far away up to find the mass of this. So mass of this will be 2.4 kgs. Okay. Yeah, 2.4 kgs. So this mass is 2.4 kg. Okay. So uh, it rebounds, and no, sorry. This velocity is not known to us. We have to find it. I'm calling it V1. We have to find it. So by first applying, like, why it is not equal, because if it is equal to 4.3, it means that all of the kinetic energy which was earlier with the body, that is taken away by the body. So what kind of energy is given to the block? Obviously this velocity has to be lesser than 4.3. So we have to first find it. So we will apply the conservation of linear momentum principle. So before the collision takes place, the momentum of this is 0.8, or we can first write m1 u1 m2 u2 will always be equal to m1 v1 plus m2 v2. Now u2 is 0 because the block is not moving, but this is not 0, so we are now going to substitute this value here. M1 is again 0.8, but V1 we don't know. Now M2. Okay, now see, this body is now moving in the opposite direction, so there will be a negative sign also there, because these all are vectors. So one sign will be taken positive, another direction will be taken as negative. Now M2 is 2.4 kg, velocity is 2.16, and it is in the positive direction. Accordingly, we can find the value of V1. So 0.8 V1, it goes to the other side. 4.3. Accordingly, we can find the value of V1. So, okay, I would be using the calculator given in my mobile phone now. Just a moment. 2.4 multiplied by 2.16 minus zero point 0.8 multiplied by 4.3. So I am getting the answer of 1.74. Yeah, 1.744, which will be further divided by zero point 0.8. So this divided by zero point 0.8. So the answer is 2.18. So it is going back with the velocity of 2.18 meter per second. Now clearly I can say that yes, the velocity is now lesser than 4.3, so kinetic energy is now shared by both of the bodies after the collision. Now the very next step is that we have to find the total kinetic energies. So let's see that. Now I'm going to erase these things now. Okay, so we will find the initial kinetic energy. So initial kinetic energy is half into m into v square, which will be, it will be taking a lot of time like this. I think we should start referring to uh, the mark scheme only. So the kinetic energy is 7.396 joule, and what is the kinetic energy final. So final, we would be taking both. Like now the kinetic energy is scalar quantity, so it doesn't matter whether the body is going into positive direction or the negative direction. So half into 0.8, and the velocity is 2.18 given here, plus half into mass is 2.4, and the velocity is 2.16 square. So we have to see if these two values are coming out to be equal or not. Okay, so let us see. Yeah, so I am getting this answer as 7.49 something. But anyways, this will be treated as like approximately equal to each other, because there will be some problem with the calculators also, like how are you calculating significant figures and all that. So anyways, no problem. But approximately they are coming out to be equal to each other. So we can say that yes, it is completely elastic because the initial kinetic energy is equal to the final kinetic energy. Okay, so this can be taken as 7.4, this is 7.5, approximately they are equal. Yeah, so this is it, this is my answer. Let us go for the mark scheme and see what are they doing in the answer. Okay, so B1 clearly use the conservation of linear momentum and find the speed as 2.16. So they have just written that you have to do it like that. So we found it, that is 2.16. Now initial kinetic energy is 7.46, and the final kinetic energy is also coming out to be 7.46. For me it was coming out to be 7.4, this was coming out to be 7.5. Anyways, so it means that both of the kinetic energies are equal to each other, so there is no loss of energy involved, hence the collision is perfectly elastic. Let us now move to the other question. Calculate the maximum height risen by the center of the ball. Okay, so what is the height that it has gone up? So yeah, this was my previous calculation, and the velocity now is 2.18 after the collision. So they want to know like what height will be attained now. Obviously that height will not be equal to 95 centimeters now, so we have to see. So we will clearly, again we are going to equate the kinetic energy of the ball with the potential energy, because after some time it is going to stop. So we can directly go for v is equal to root of 2gh also, and from this equation we can find h. Or if you want to create the complete equation, uh, half m v square v1 is equal to mg. I'm just going to call it h1 now. So m and m gets cancelled out, so half the velocity is 2.18 square divided by 9.8, and this will give you the new height which will be accomplished. So anyways, not going to calculate this thing now. I would be going directly to the mark scheme and show you if they are doing the same thing. Yes, so the speed is halved. Okay, so here they're directly saying that the speed is halved, so the height is halved. But otherwise, you see here, use the conservation of energy. Half mv square is equal to mgh. This is what we have done. Okay, and accordingly we will find the height h, which will be coming out to be equal to 23.8. Yes, of course there are other methods also, like there is a quicker method. You can clearly say that the velocity is now half, so it will be 1 by 4th. So now your height is 1 by 4th now. And you can even use the kinematical equations, because but I will not suggest you to do that. This is the best method that you can employ here. So 1b2 is done. Let us go for 1c now. Okay, yes, this will be the last part. Coefficient of dynamic friction between the block and the rough surface is 0.4. Estimate the distance traveled by the block on the rough surface. Okay, so what was the data that we were earlier having? Yes, now you see. So this the block is now having a velocity of 2.16. So again, I'm keeping myself to work energy only. So according to the work energy theorem, the work is always equal to the change in kinetic energy. So here the kinetic energy is changing. Earlier it is moving with the velocity of 2.16, but later the velocity becomes 0. So we can say that all of the kinetic energy is lost. So half m v square. It is lost. But where is it lost? Somebody has done work against the motion. Friction. So friction work is like friction multiplied by the distance that will be traveled, because here there will be friction here, and the displacement traveled you can take like this. So this will be the distance d. So f into d is the negative work done, but we are only concerned with the magnitude here. So this will be equal to f into d. Clear? From here we can find, like, see, mu is given, we will find the distance d. Okay, so this is equal to, friction is 0.4 into m into g, because that is going to be the normal reaction here, isn't it? And d, from here we will find d. So 1.2 multiplied by 2.16 square divided by all this. So again, we will not be calculating this thing, and from here we will find the distance d. Let me show you what is happening in the mark scheme. Yes, this is the question of, so frictional force is mu mg. So they first find the friction that is acting on the body, and this friction multiplied by d is work done against friction, that is equated with the loss of kinetic energy, half mv square. Clearly this is exactly same thing that we have done, and so the distance traveled will be 0.594. So I think accordingly we can say that yes, this question is now clear, like we have done this question properly. So this is what will happen. So you could go for the Stewart equation also, but again I would be preferring you this thing. It's very easy, and it will give you the answer directly. Okay, dear students, so hoping that it is going to help you people, and you would be sharing this video with all your friends. Okay, thanks for joining the YouTube channel. All the best. Bye. See what is there in this question now. A solid piece of chocolate of mass 82 grams is placed in a pan over fire. Thermal energy is transferred to the chocolate at a constant rate. The graph shows the variation with time t of the temperature t of the chocolate. At 6 minutes, all the chocolate has melted. So at this point, all the chocolate is melting. Okay, so this is about the latent heat, and this will be about the sensible heating. Yes. The specific heat capacity of the chocolate is given. Show that the average rate at which the thermal energy is transferred to the chocolate is about 15 watt. So we have to comment on the rate. Okay. So first of all, what do you mean by this rate? And the specific heat is given, the latent is not given. So we would be concentrating here. What is actually happening in the question? You must know how to read the graph first of all. So let us first of all see how many divisions are there. 1, 2, 3, 4, 5. So clearly this is 35, and 1, 2, 3, 4, 5. Yeah. So this is 31 degree C. So you start, the chocolate is at 31 degree C, and it's in the solid state. So it means that the melting point of the chocolate is 45 degree, and first of all it will become solid at 45, and then it will become liquid at 45 degree. So this is what is latent heat is happening here. So A, B, C. Specific heat is given to you. So latent heat is not known to us. So obviously we will not be concerned with B and C. Otherwise it could be very easy for us. But anyways, so this is specific heat capacity that is given. So we will concentrate on region AB. And we want to find the rate at which the energy is given. So we can first find the total heat, and we can divide it by the total time that was taken by the chocolate to increase the temperature by some certain degrees. So if I compare A and B, the temperature can be taken to be like 31 degrees centigrade, and it increased to 45. Okay, so Q is equal to MC delta T. So we will first find Q. Mass is given as 82 grams. So it will be 82 divided by 1000. into specific heat, that is 1.6 10 raised to power 3, and it is multiplied by the change in temperature, which is 45 minus 31. So 45 minus 30 is 15, and we're subtracting 31. It means it will be 14. So your like this and this gets cancelled out. So your answer will be 82 multiplied by 1.6 multiplied by 14. And my dear students, those who are confused with the like how I am finding delta T without converting temperature into Kelvin, so to them, if you are concerned with delta T, that is the change in temperature, whether you go for delta C in degree C or you go for Kelvin, you would be getting the same answer. Like let us say if I convert these temperatures into Kelvin, just for the sake of clarity, 45 will become this, and 31 will become 273, will be added like this. 273 and 273 will get cancelled out. Again, the answer is coming out to be 14. So whenever you are concerned with delta T, there is no need of conversion of the temperature scale from degree centigrade to Kelvin. But by the way, if it's not degree centigrade, but Fahrenheit is given or something else is given, then definitely we have to convert it into Kelvin. Anyways, so this is it, and the answer for this is 82 multiplied by 1.6 multiplied by 14, which is 1836.8, and we can say that it will be, the answer will be in joule, because all of the units are in SI, like joule per kg per Kelvin, and so everything is cancelled, so this answer will be in joule. Now we are interested in the rate at which the energy is given, so we have to divide this much of the energy by the time it has consumed. So from A to B, the time consumed is 2 minutes, so 2 into 60. So our answer will be uh, like where to write, just a moment. Okay, so we want to find the rate now. So the rate is 1836.8 joule divided by the time. So it is 2 minutes into 60 seconds. Yes. So that will be this divided by 120. So our answer is coming out to be 15.3. You can call it watt or joule per second. One is the same thing. So this is the rate, and this is the first part, like 2A. This is how we do it. And let us move to the part B now. And before we go there, let us see the answer, if we are having the correct answer. And yes, the answers are here. 2A, the answer is 15 watt or 15.3 watt. And they seems to have done the same method. Let us now go for the second part. Estimate the specific latent heat of fusion of chocolate. So now we want to comment on the latent heat of fusion. Estimate the latent heat of fusion. Okay, no problem. So what we do in this, we would be concentrating on uh, B and C. So the power or the rate at which the energy was given is 15.3 watt, and we will find Q is equal to M into L is the formula. We want to find the L. Q is the heat that was given during the process BC. So the heater is providing energy at 15.3 watt. The time consumed is 6 minus 2, that is 4 minutes. So the energy that is given is 15.3 into 4 minute into 60 seconds. 4 into 60 seconds. This will be the energy that was given, and that was taken up by mass and the latent heat. So that will be 82 divided by 1000 into the latent heat, that is L. From here, we are going to find the value of L. So this value is already known, multiplying it by 4 multiplied by 16 and dividing it by 0.082, isn't it? Yes. So this is the answer. So the latent heat for us is, and the unit will be joule per kg. Yes. So we can write it as 44.8 kilojoule per kg. That's it. So this is the latent heat. Okay, 44.8. Let us see what is the answer. Um, 40, yeah, I got 44.8, so 45 kilojoule. So they are giving 4.5 into 10 raised to power 4, just another way of writing the same thing. So B part is over now. Let us go to the C thing now. Okay, so the C question is, compare the internal energy at t is equal to 2 minutes and t is equal to 6 minutes. Okay. Yes. Now, internal energy at t is equal to 2, and at this point it is the internal energy at t is equal to 6 minutes. So clearly, some energy has been given to the chocolate, to the material, and the material has taken up that energy. So clearly, the internal energy increases. So the first argument that we are going to make is that internal energy increases. But what happens of this internal energy, whether it is going to increase the kinetic energy or whether it is going to add up into the potential energy? So if we talk about the point B and the point C, they have the same temperature. So by the kinetic theory of gases and the formulas that we have, accordingly we can reach to this conclusion that because the temperature is same, we can clearly say that there is no change in kinetic energy. So the second statement is no change in kinetic energy as the temperature remains same. Now, as the temperature remains same, there is no change in kinetic energy. So, where is this energy going? Obviously, it is used in increasing the potential energy. So, we will say it is used in increasing potential energy only. So these are the three statements that we can make about the internal energy. This is what is happening. Let us go for the answer scheme now and see what is the answer that they have given. Internal energy is greater at 6 minutes, or the internal energy is lower at 2 minutes. Internal energy increases. Yeah, this is the first statement that we made. Now, because kinetic energy is the same, potential energy increases. So there it is. So this is the second question for May 2023 time zone 1. Let us see what is like, how are we going to solve the next question in the next video. Till then, all the best. Bye. Is there in this question now? A transverse water wave travels to the right. The diagram shows the shape of the surface of the water at the time t is equal to 0. Now, if the diagram shows the shape, literally the shape of the wave, it means like you have actually clicked an image there. So this is definitely a wave like this. The diagram that they have made, it is consisting of multiple particles, I mean to say. So in such a cases, on the x-axis you have distance, and on the y-axis you have the displacement, and that is what is there. So p particle is different and q particle is different. So p and q show two cocks floating on the surface. Okay, fine, no problem. So the first question is, state what is meant by a transverse wave. So that's an easy question, I would say. You can clearly say that transverse wave is a wave in which the particles are oscillating in a direction perpendicular to the direction of the wave in which energy and momentum is being transferred. It means that, like, let us say we're talking about the particle p. So particle p will be moving like up and down, but the wave is moving towards right. So there is the 90-degree angle, the right angle between the direction of the wave and the direction of motion of the particle. So I think that is that must be already known. There will be no doubt in this question. Okay, let us go to the next question. Like, what are they asking? The frequency of the wave is given 0.5 hertz. Calculate the speed of wave. Okay, frequency is given and you want to find the speed of wave, and the distance is also given. So the speed of wave is equal to frequency into wavelength, a very simple formula, and we would be using this. So the speed of wave is not known, the frequency was zero point 0.5 hertz. And the wavelength, from this diagram we can find two things. Number one is the amplitude of the wave, and number two is the wavelength. So wavelength is coming out to be 15 and the unit is given meter, so it will be 15 meters. Clearly 7.5 meter per second will be the velocity with which it is moving. Okay, frequency is yeah, so for one oscillation is done in half second. Yes, 7.5 meter per second. Yes, so this is the velocity, and let us verify it from the mark scheme. By the way, the answer should be correct. Oh, they're taking it to be 16. Let me see. Oh, okay, I'm really sorry for that. I didn't see it. So 1 2 3 4 5 6 7 8 9 10 11 12 13 11 12 13 14 15. Oh my god, so this is basically 16 meters. My fault, my mistake, my dear students. So it is 16 meter. Be very careful about this. So doing it again, so zero point 0.5 into 16, so that becomes 8 meter per second. Anyways, so let us now move to next question. Plot on diagram the position of P at time t is equal to zero point 0.5 second now. So position P at time 0.5. So this is the position shown at t is equal to 0. We want to find the position at 0.5 seconds. So the frequency is 0.5. From here, we will first find the time period. So the time period for this is 1 by 2. It means that it is 2 seconds. So 2 seconds. So if I'm now going to talk about the particle P, you see the particle P, like this motion is going towards right hand side. So particle P would be going up. So particle P goes up and then it would be coming down. It will go further down and then it will go further up. Okay, so basically it is traveling a distance of 4a and the time taken is 2 seconds. But we want to talk about the time which is 0.5 second. So clearly we can see that it means that it is 1/4 of the journey that will be over in 0.5. It means that the particle P will reach at this position. So particle P will be at the positive amplitude. And now I would be very careful about one. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is 1, 11, 12. So this is 1.2. Yes. So it is 1.2 meters above the mean position, you can say, or you can say that it is at the amplitude. So this will be the answer. Okay. Let us see how are they doing it. Yeah. So here, yes, even they have done the same thing. So the point P will be 8, 1.2. So the position will not change. So the x position of the point P will not be changing, but the height will become 1.2. Okay, so this is done, and this is done. Now we would be going for A4. Okay. Show that the phase difference between the oscillations of the two quarks is pi radians away. Okay, so the phase difference is pi. We have to prove this in the point P and Q. How are we going to do that now? So phase difference. Okay, so phase difference. So clearly, whenever you're talking about 2 points like P and Q, so we know that the phase difference will be pi, but we have to prove it somehow. How are we going to do it? There is a formula for this. That formula is kind of hidden, I would say, like nobody is talking about that, and generally, and it is not even present in the data booklet, not even in the books properly. The formula goes somewhat like this: delta phi is equal to 2 pi divided by lambda wavelength into delta x. Although it's just a mathematical formation by using the unitary method, that for the lambda wavelength 2 pi is the phase difference, accordingly we can create this formula. But anyways, if you people want to remember it, that will be really useful if you remember it. Okay, now you see what is the delta x. Delta x is the change in position, the difference in position of 2 points like p and q. So this is 5, 6, 7, 8, and this is 16 as we have seen it earlier. So the position difference between P and Q is 16 minus 8, that is 8 meter. We will be putting this value here, knowingly that the wavelength of this is 16 meters. So it will be 2 pi into 8 divided by 16. So this will be 2. This 2 and 2 gets cancelled out. And from here clearly we can see that the phase difference is equal to pi. This is how we can show it, we can prove it, because otherwise it's just known to us. Like if there are two particles which are placed the way P and Q are placed, we know that the path difference is lambda by 2 and phase difference is pi. But how to prove it? You can prove it by using this formula. Okay, so let us see what they have done. I think they have done the same thing. Yeah, the phase difference is 2 pi by lambda into this. Again, they are not giving any formula here, but this is a very useful formula and it can be used at many places. So if you remember it, that will be highly useful. Okay then, so let us move to the next question. Okay, so now we have a different statement. Monochromatic light is incident on two very narrow slits. Okay, so first of all, monochromatic means that the light which is coming, it has a uniform wavelength. It's not a mixture of two or three radiations, as is the case with the diffraction grating, but it is clearly the case of interference. Now, two narrow slits, it means that we would be talking about the interference rather than the diffraction, or interference overlapped with the diffraction pattern. So that we will see. The light that passes through the slits is observed on a screen. M is directly opposite the midpoint of the slits. X represents the displacement from M in the direction shown. Okay. So the student argues that what will be observed on the screen will be the total of two bright spots opposite to the slits. Explain why the student's argument is incorrect. So definitely, see, like what usually happens is, like what you can expect. Let us say there are two walls here and you have one bulb here, and then you see that the I don't think that the light is enough. So what you do, you install another bulb nearby. So what do you expect out of it? You would be expecting that the intensity of the light on the wall will increase, isn't it? And there is nothing else that you expect. Do you expect that there will be an interference pattern? You, if you literally do this experiment at your home, would you be able to find an interference pattern? Of course not, because there will be some conditions that you have to meet before this kind of thing happen. So the student here, he argues that this kind of thing will happen even in this case. But in this case, we have completely satisfied the conditions that we need for the interference. So instead of doing that, interference will be happening. And instead of having a uniform distribution of double the intensity on the screen, we are going to see a pattern there. So you have to just write what is interference. You have to say that because light is a wave, so the interference will be taking place. And so at point M, there will be a bright spot, and then it will be followed by a dark spot, and then there will be first bright, then again dark, then again bright, then again dark. So there will be alternative fringe pattern of a bright fringe and a dark fringe. So that kind of pattern will come here because of the interference that is taking place. Because of the interference that is taking place. Anyways, let's see what is the answer given in the in here. So this is 3B. Okay, we would be going for 3C, no problem. Light acts as a wave and not a particle in this situation. Light at slits will diffract, or they are calling diffraction pattern, but if you talk about the interference, even that is not wrong. Light passing through still slits will interfere and create an interference pattern, creating bright and the dark spots. So this is what we have to write. Okay, so moving to the C part now. Okay, so C part is about this. The graph shows the actual variation with the displacement x from m of the intensity of the light on the screen. I notice the intensity of the light at the screen from one slit only. Okay, explain why the intensity of light at x is equal to 0 is 4 I naught. Okay, so it's kind of theoretical question only, because when you do this topic, you learn about these things. So the first point that I would like to make here is that we can clearly see that the intensity pattern is not modulated. It is not modulated. So if this is not modulated, it means that only and only interference is considered, like pure interference is there. We are not considering diffraction that should be taking place because of the slits, isn't it? Because you can't get rid of diffraction at the end of the day. It will be there, you can minimize it, but you can't get rid of it. So but in this case we can just say that we are not considering that. So this is not modulated. Now this is the intensity that is shown here, but with respect to the original intensity of one slit, this intensity is 4 times. Now why that will be? Okay, so there is the formula that we did, I think, in topic 4, that intensity is directly proportional to the square of the amplitude. So if you're considering only one slit, the amplitude of the wave that will reach the screen is A, that is going to be this, and I'm just calling it I1. And in the second case, the amplitude doubles because the constructive interference is taking place at M. So this is 2A square. And so by using the principle of proportionality, we can clearly say that it will be like this. So I2 is the new intensity and I1 is the original intensity of one slit. So clearly by using this principle, we can prove that yes, this will be equal to 4. By using the proportionality conditions, we do not even know the formula for this, and we have still done it. So this is how this question will be done. Let us see what they have done in the mark scheme. Yes, they have just written it instead of showing it mathematically. The amplitude is doubled, so intensity is proportional to to the square of the amplitude. That is why. So let us go for the next question. It's a very long question, I must say. Okay, so the slits are separated by a distance of 0.18 millimeter. So this is small d. The distance between the screen is this. So this is capital D. Determine in meter the wavelength of the light. So we have to find the wavelength. Okay. So in this case, what we do, we are going to use the formula for the spacing, and that is this. And the spacing is defined as the distance between the two maximum points in the interference pattern. So this is the formula that we would be using here. So in this from this diagram, we are going to find this distance, but now this, like, we cannot be very sure about it, like what it is, isn't it? Because this is in between, you see. Let me maximize this thing, like, you see, because this is actually kind of input. So we are not sure about what value should we use here. So there is a method in which we can become 100% sure. How? We have to count, like, okay, this is a perfect point and this is also a perfect point. How many wavelengths are there? 1, 2, 3, and this is exactly half. So it's 3.5 wavelengths, or 3.5 distances, fringe width, and the distance is 2 centimeters. So if I take it like 2 divided by 3.5, so this should be equal to the fringe spacing, isn't it? 2 divided by this, or we can do this also. You can count like, you can take 4. So 1 2 3 4 5 6 7, and 4 divided by 7, so exactly the same thing that I have done earlier. So we can take it as 4 by 7 x. Please try to understand here. We are going to find the spacing here. So what we did, we found the total spacing and we counted the total number of spacings and the total number of fringes, you can say. We divided the total distance by total number of fringes to find the distance of one fringe. So that is 4 by 7 centimeters. It means that the answer here, 4 by 7, because it is centimeter, we will multiply by 1 by 100. Wavelength we want to find, capital D is 2.2 meter and small d is given in millimeters. That has to be converted into meters. So this is it. And so this is how we do this question. Um, Instead of calculating, we can, okay, I will show you on the calculator now. Divided by 2.2 into 10 raised to power negative 3 and negative 2, so I have clubbed it. So this will be 4 divided by 7 multiplied by 18 divided by, okay, 2.2 divided by 100. I forgot the decimal. So the answer will be 0.04 meters. So in meter, this is your answer, because everything in meter, and they want you to answer in meter. So you can definitely create it. You can write it like 4.6, so two zeros, 10 raised to power negative 7 meter. Yeah, so this should be the answer, 4.6 10 to the power negative 7. Let us see what is the answer given. Yes, 4.6 10 raised to power negative 7 meter, exactly the same way that we have done. Okay, so let us move to the next part now. Indeed, this is a very long question. Some questions in paper 2 are very short and some questions are really very long. They take nearly 20 minutes or like 25 minutes. Even I take that much of the time. Like obviously students would be consuming a lot of time in these questions. The two slits are replaced by many slits. Okay, of the same separation. State one feature of the intensity pattern that will remain the same and one that will change. So first of all, we must understand what do you mean by this question. So what happens is, like, this is the diagram here. So what they say is that now they have increased the number of slits, but without changing the spacing between the slits. So D is not changed, but the number of slits have been increased. Like there is one more here, one more here, one more here. Accordingly, we can say one here, one here, one here. So now the total 1, 2, 3, 4, 5, 6, 7, 8. Total 8 slits have been created now. Now, in this kind of a question, D is not changing. Okay, so we have to find like what will happen now. Couple of things happen in these kind of cases. Number one, the intensity pattern, like earlier it was 4, but now it will not be 4. The ratio of I divided by I naught was coming out to be 4, but this time it will not be 4. Why? I tell you. In that case, there were only two waves, so the amplitude was becoming 2a, and intensity was directly proportional to 2a square. So I told you that it will become 4 times. But now the amplitude is 8 times. 1, 2, 3, 4, 5, 6, 7, 8. It means at m, you have 8a as the amplitude. So by using the same formula, same principle, that intensity is directly equal to square of this, it means that intensity for these eight slits it will be 64 times the individual intensity. So in this case, I by I naught is going to become 64. Earlier it was I by I naught is equal to 4 in the case of two slits. This is in the case of 8 slits. And mind it, 8, I have just taken an example. They are saying many slits. This is what happens when you have many slits. What else? What else? The formula for the spacing that we just used is lambda d by d. Do you think that there is anything that is changing in this? Are we using a different wavelength? No. Are we messing up with capital D? No. Capital D remains the same. Are we messing up with D? Small d? No, not at all. It means that in this interference pattern, spacing is not going to change. It means that this is also going to be an interference pattern with the same spacing. Only the thing is that the central maximum would be having a very big intensity now. It will be very, very sharp intensity. Okay. So, what are the things? Like the question was, what will change and what will not? So, point number one, the spacing will not change. And point number two, the maximum intensity is going to become 64 times, like it will be very high. Let us see the question once, and then, yeah, two slits are replaced by many, stays the same. So, spacing will remain the same, but the intensity divided by I naught will become different. Let us see the answers now. Yeah, stays the same. Position, location of the maxima, distance, separation between maxima, that will be the same. So the interference pattern is actually going to look similar, but intensity or the brightness, width will become lesser, intensity will become high, it will become sharper. So that pattern, like it was broader earlier, now it will become like a pin, it will become thinner but longer, so it will be a pin kind of thing now. So maximum will change. So these are the two things, and they are still, I would say, like nothing different in this, because that is the part of our syllabus. And if you go to the book like Sokos or Oxford, you would be finding each and everything written there as it is. So it's from that, like no, like nothing as unusual here. Okay, so again, the question is very long. Let us go for the part D now. D1. Two sources are viewed through a single slit. Okay, two sources are viewed through the single slit. Okay, so now I think this is a different statement, so different question. Now they are moving to resolution. So this topic is going to test each and every concept and each and every topic for you. A complete 9 and complete 4 has been taken up. Okay, so two sources are viewed through the single slit. The graph shows the diffraction pattern of one source. Okay, so this is kind of one star and you are going to watch two stars. So I'm going to draw a very simple diagram here. Like this is the lens. These are the two stars, and this kind of pattern will be there. So this is the image number 1, and this I can say is the image number 2. Yeah, so this is star 2, this is star 1. So this is what is happening. So my dear student, I believe you would be able to understand what is this. This is the distance between two stars. I have chosen it to be x, and this distance I choose it to be L. This is the device which is used to see the two stars. It could be a telescope, it could be like, if you're talking about some other thing like two aircrafts are coming, it could be a radar, whatever, but this is the measuring instrument, and it is having circular aperture. Okay, that is also a condition, it is a circular aperture. Now, I1 is the image of the one star. And this is the central maxima of the first star. This is the central maxima of the second. Like this, they have given. So we can say this is like kind of I1 or I2, one star, anything. Sketch on the axis the diffraction pattern of the second star. Okay, so fine. This was about the background information. Let us now see what they want to ask. Sketch on the axis the diffraction pattern of the second source when the images of the two sources are just resolved according to the Rayleigh criteria. Now, what is the Rayleigh criteria? Rayleigh criteria is that they will be just resolved, the images will be just resolved if the central maxima of star 1 or any star, it overlaps the first minima of other. Clear? So let us say this is the image of one star. So technically there is one star, and when you use a telescope or something, there has to become one image. But because of diffraction, it is having one bright image but other less brighter images, but there will be like 4 images or 5 images. Okay, so there will be 5 images. So these are 5 images there. Now, so what happens now is we want overlapping pattern. So this is the first minima for this star. So the maxima of the second star will come here, and the minima will be overlapping here. So it has to be somewhat like this. Like this. So you can count 1, 2, 3, and 4. So 1, 2, 3, 4. So here it will be the minima of this, and here the second minima, like this, and then 4, and then 1, 2, 3, 4. So it will be 1, 2, 3, 4. This will be another minima. Like this. So this is going to be the another pattern that will be drawn for the second star. And let's see how they have done. Yes, they have done the same thing. So clearly you can see the formation here. So the minimum here is overlapping the maximum. The minimum here is overlapping the maximum. Here both of the minimas are there. Both of the minimas are overlapping. So these two stars will be resolved according to the Rayleigh criteria, and this is it. Okay, let us go for the next question now. Okay, just a moment, please. Okay, so Centaurus A is a galaxy a distance of 1.110 about 23 meters away. A radio telescope of the diameter of 300 meter operating at a wavelength of 3.2 centimeter is used to observe the galaxy. Determine the minimum size of the radio emitting region of the galaxy that can be resolved by this telescope. Now this question, when you read the statement, looks very complex, but it's not that complex. Let me explain you this. So there is a galaxy there, and again we are just concentrating on the two stars, like what is the minimum distance that the stars can be so that they can be resolved properly. This is the distance, so this is the L. I have drawn the diagram earlier, I would be drawing that again. X is basically unknown, the radio telescope, and this is the diameter of the aperture I was talking about, like whether it is telescope or a radar or whatever. This is the wavelength that is being used there. So determine the minimum size of the radio emitting region of the galaxy. So you have to find like the minimum size, like the distance between two stars that will be resolved. So what are these symbols now? Let us say these are the two stars. So this distance between the two stars is x, but the distance between this and this lens, this is capital L. Like this. And so this distance, so this is the diameter, which is small d, like 300 meters. Wavelength is lambda. And now this is the diagram. So I usually refer to this question as, like, like bigger triangle and smaller triangle. So you see, this is a bigger triangle which literally goes away. Like, it is one side of this is capital L, which is 1.110 raised to power 23 meters. Like, it is that bigger triangle. That is why I'm just calling it bigger triangle. And this triangle is very small. The triangle is within the telescope or within the retina, or you getting my point? Like, this is kind of lens and this is the screen where the image is created. So this is a very small triangle there. And now this is the theta that we are considering here. Now when it comes to the resolution, the Rayleigh criteria, I told you that this will be the central maxima and this will be the first minima. Like, if I'm going to talk only about the images created by one star, so that will be, this will be the central maxima and this is the first minima. So this is the theta. So theta is equal to lambda divided by b. So because it is the case of diffraction, so we'll not call it d, we will call it b. That, well, like, just like terminologies, d is used in interference, so to differentiate we just use b. It is lambda by b. And this theta can be taken from the bigger diagram also. Like, tangent theta is x divided by L. Here also in the smaller triangle you can also say, like, this is this fringe spacing S and this is this, but yeah, this will be lambda d by small b, and this is usually capital D. So when you find the tangent theta here, so this capital D will be getting cancelled out. So you can still say that the tangent theta is equal to lambda d by b divided by d. So you would be anyways getting the same formula. I think this much should be either known to you or that should be given in the data booklet. Some couple of formulas will be given in the data booklet. You can refer to that. Now, from this, because theta is very, very small, so now a bit of maths AAHL. Tangent theta is equal to theta. So this theta is x by L. So we have two statements here. Theta is equal to lambda by b and theta is equal to x by L. So we have a very beautiful formula. X by L is equal to lambda divided by b. A very easy, but we need to understand what is this. You can just plug in your values and we can get the answer. But there is another factor which is 1.22. I forget that. Just listen to this now. So this formula is correct, but it is correct only for rectangular slits. Like, this is for rectangular slits, so everything is fine up to this. But we are using a circular aperture. Like, the radio telescope diameter is given 300 meters. It means it is circular aperture. It's not a rectangular aperture. So the formula is not valid. So how to make it valid? There is a constant that has to be multiplied. So our overall formula becomes 1.22 lambda divided by b. That's it. And from this formula, we can find the value of x. Okay, so I have explained you each and everything in this question now. So we just plug in our values and we get the answer. So instead of doing this thing by myself, I will refer to the mark scheme now because it's already half an hour for this question now. It's really, really big question, I must say. So d by d, so I have used this is as x and this as capital L. They are using d by d, which is a highly misleading statement. 1.22 into lambda by b, exactly same thing. Plug in the value, get the answer, game over. So this is how we do this question. So 3D2 is over. Let's see if the question is over or not. And yes, the next question is question number 4, and that will be done in the next video. So this is how we do this question. It was indeed a very long question. All the best, my dear students. Thank you for joining the YouTube channel. Bye. Students. Okay, dear student, let us see what is there in this question now. A cell of negligible internal resistance and electromotive force 6 volt is connected to 3 resistors PQR. R is an ohmic resistance and IV characteristic of P and Q are shown. So these are non-ohmic and the characteristic is shown here. Okay, so the graph is shown. The current in P is zero point 0.4 ampere. Show that the current in Q is 0.45. Current in P is zero point 0.4 and Q is 0.45. So P and Q. Okay, so the graph is given here, and so you can clearly see that these are non-ohmic. Let me explain you what is an ohmic resistance and what is a non-ohmic resistance. Ohmic resistance is the resistance that follow the Ohm's law. What is the Ohm's law? V is equal to IR, which clearly means that the graph between V and I will be a straight line passing through origin. So it has to be like this. If it is not this, it is non-ohmic. So definitely P and Q graph is coming out to be curvilinear graph between I and V. So that is not good. So this is non-ohmic resistances. These are okay. Now the current in P is shown as zero point 0.4 ampere. Here it is 0.4, and you talking about P. So the voltage across P should be, according to this graph, it should be this. What is this value? 1, 2, 3, 4, 5. So it's basically 1.4 volt. Yes. So 1.4 volt is the potential difference across P. 1.4. So 1.4 is the potential difference across P. So that will be across R also. So the potential difference here is 1.4. Total potential difference is 6. Clearly, Q would be having a potential difference of 6 minus 1.4. So 6 minus 1.4 is 4.6. So 4.6 volt is the potential difference across Q. So you want to find the current now. So 4.6. Yes. So voltage is 4.6 now. 1, 2, 3. This is 4.6. And so the current in Q is here. It is this. So it becomes um 0.4. This is 0.5. So this is 0.45. 0.45 amperes, absolutely correct. This is 0.5 mark, this is 0.6 mark, so this will be 0.45. So clearly we can say that yes, the voltage will be this. So do you get it what I did? Because those two things, they are basically in series, we can say. Actually they are not in proper series, but as per the potential difference is concerned, definitely this will be having V1, this will be having V2, which will be across P as well as across R, the potential difference. So V1 plus V2 will be equal to 6 volt. And clearly this is the way that we would be doing it. Let us see what they have done. So question number 4, the potential difference across P is 1.4. So the voltage across Q will be 6 minus 1.4. And so this is this, and accordingly we can find the current which is passing through the Q. So that is coming out to be 4.5 amperes. Let us now move back to our question. Uh-oh. Okay. Just a moment, please. I have to get rid of these windows. Okay. So let's go for the question number 2 now. Calculate the resistance capital R. So calculate the capital R. Okay. So we have now created the new data for ourselves. Like the voltage difference here is 4.6 volt, and this was coming out to be, this was 6 volt. So it was 1.4 volt. Yeah. Yes. So we want to find the resistance of R. So the voltage across R will be 1.4. The current we can find, like the total current is which is coming into this, like passing from Q, is 4.6. And the current which was in P, what was the current? We found that current. No, this is the problem with the paper 2 questions. No, like every other time we have to see current in P is 0.4. Okay, 0.4 and 0.45. So the current here is 0.05 ampere, and the voltage across this was, I have forgotten that now. I think it was 1.4 volt. I tell you, these paper 2 questions, no, like they are not only about the hard disk, like how many formulas that you remember, it's about your RAM also, okay? So how many things you can keep it here. So it will be 1.4, so the resistance will be 1.4 divided by 0.05, so the resistance will be 28 ohms. So that will be the answer. Let us go to the mark scheme and see if that is the correct answer. And yes, it is indeed 1.4 divided by this, so that is 28. Let us now move to the next question. Calculate the total power dissipated in the circuit. Total power dissipated. So for the total power, we should be concentrating on the battery. That is the power which is given by the battery. So the total power given by the battery will be equal to total power consumed. So the voltage is 6 volt and the current which is coming is 0.45 volt, sorry, amperes, isn't it? 0.45 ampere, the current which is coming from this. So the power formula is V into I. We are concentrating on the power given by the battery. That will be our answer. 6 multiplied by 0.45, 2.7 will be the answer. So 2.7 watt is the power given by the battery, which will be equal to the total power consumed by the circuit. The other method is to first find all of the resistances, then you find the R equivalent or R total, and then you will apply the formula I square R to find the total resistance, total power. So you can use 2.7, like P is equal to VI. It's better if you're concentrating on the battery. So the answer is 2.7. And let us see what is the answer here. Yes, even they have done the same thing. V into I, that is 2.7 watt. Okay, so this is how we do this question. Let us go to the other question now. Resistor P is now removed. Suggest without calculations the effect of this on the resistor of Q. Now P is removed. What is the effect of this on the resistor of Q? Okay, so P is now removed. What is the effect of this on the resistance of Q? Okay, so P is removed, which clearly means that the R equivalent will increase. It will be having more total resistance. See, when the two resistances like P and R, these two resistances, they are in parallel to each other, so their equivalent resistor will be minimum, like it will be lesser than the minimum of the two. So the resistance for P and R will be very less. Later, that resistance will be added into the resistance of Q to create the total resistance. Now, if P is removed in the first place, so R is not going to be reduced. R will be giving you a big value, which was coming out to be, I think, 28 ohm, I think. If it was 28 ohm, so only and only 28 will be added there, no? So R total now will be the sum of Q and R, so that will be bigger. If this resistance will become bigger, it means that the current which is flowing here will become lesser, isn't it? Because the total current will be total voltage divided by total resistance. Now you have a bigger resistance, the current will be lesser. So the current which is passing through Q will be lesser. Earlier it was 0.45 amperes. Now it will become lesser than this. So what is going to happen? Let us go to the graph now. And you can clearly see that if the current is reducing here, so if the current is reducing, the slope is increasing. Like here, the slope was like this. Gradually, the slope is becoming steeper. And now this graph is I by V. So in I versus V graph, the slope of IV graph will be equal to 1 by R. Try to understand. The slope of VI curve is R. This is I by V. The slope is I by V rather than V is equal to IR. The slope I by V is equal to 1 by R. That is why. So more is the slope, lesser is the resistance. So if the current is reducing, the slope is becoming bigger. It means the resistance will become lesser. So even for Q, the slope is becoming like this, isn't it? Like slope is increasing. So the resistance of Q is going to increase. So this is the explanation. Let us go and see what is given in the mark scheme. Q will have a smaller resistance. The slope has increased. Sorry, earlier I said it in the wrong way, but I meant the same thing. Slope is bigger in the case of Q. So the slope is equal to 1 by R. So bigger slope, lesser R. So Q will have a smaller resistance. I think by mistake, in the statement when I was giving earlier, I told it that the resistance would be increasing. Slope is increasing, resistance is decreasing. Please forgive for that. You can also see if I actually made a mistake or not. I don't remember. So this is it. It means that for Q, the resistance will be smaller, but I have given you the correct explanation. Because total resistance of the circuit now will be larger, the current will be smaller. So the slope will be higher, and which means that the resistance will be smaller. Okay, dear students, so this is the explanation for this. I think the question is now over. Let us verify. Yes, there will be question number 5 after this. Yes, so this is all for this question, and now in the next video we would be going for the question number 5. Okay, dear students, all the best. Thanks for joining. Bye. Okay, dear student, let us see what is there in this question now. Question number 5. Identify with ticks in the table the forces that can act on the electrons and the forces that act on quarks. So electrons cannot have strong nuclear forces. Electron would be experiencing only weak nuclear forces. Why? Because they are basically not the part of you can say they are not quarks, or they are not the part of the nucleus itself. So strong nuclear forces act within the nucleus, and there are no electrons there, so they would be experiencing weak nuclear forces to the max, but not the strong nuclear. Quark, on the other hand, they go for all the type of interaction. They go for weak nuclear, strong nuclear, they go for electromagnetic interactions also. But by the way, electromagnetic interactions do happen in the case of electron also. So if there was another option given here, so we would be having these two ticks here also. Let us see the mark scheme, like whether the answer is the same or not. And yes, weak nuclear will be having 2 ticks, and the strong nuclear will be having only 1 tick, and that is for quark. Okay, again my mistake, sorry. There are too many windows open, and let us go for this. Okay, question number B. The following data is available for atomic masses for the fusion reaction. Show that the energy released is about 18 mega electron volt. So, okay, sorry. Yes, we would be needing a calculator now. That is why. Yes. So in this case, you see, like the mass of deuterium and tritium is given, and helium is created, and the mass of the nucleus of helium is also given. Show that the energy released is 18 mega electron volt. How are we going to do this? So first of all, we must know one thing, that 1 AMU of the mass, if it is converted into energy, it is equal to 931.5 mega electron volt. So I can say that 1 AMU is equivalent to 931.5 mega electron volt, or you can just call it that this is the rest mass energy of 1 AMU, isn't it? Yeah. Okay. So having said that, we would be finding the mass defect now in this question. So what is the mass defect? So mass defect, obviously energy is produced in this reaction, so energy is a byproduct, and which means that mass is converted into energy, which only means that initial mass was bigger. Now the mass will be lesser, which is converted into energy. So energy is more, that is present on the right hand side of the reaction, but on the left hand side energy is less, but the mass is more. So more mass minus lesser mass. So we will first find the mass of the reactant here. So that will be 2.0141 plus 3.0160. Be very careful about all the significant figures, because we have to be very, very precise, very, very exact in this calculation. This minus the total mass which is present on the product side. So that will be 4.0026, but there will be 1 also, because neutron, we can assume it to be 1, but it is not 1 actually. So the mass of neutron is 1.00. I don't remember exactly, but because there are only 4 decimal, you can just assume it 1.007. Okay, so let us see what is the mass. This, so it is coming out to be 5.00 this. So definitely this is more. Yeah. So subtracting, I'm doing calculation in other way. So don't be confused. Okay. Yeah. So my answer in the calculator is negative because I did it the other way, but we are getting the positive answer here. That is 0.0205 AMU. Now, 1 AMU is producing this. So what will be the energy produced by this? The product of these two. So our answer will be, when you multiply this with 931.5, obviously we will get rid of the negative sign here. So your answer is 19 mega electron volt. So approximately we can say that yes, our answer is about 18. So your answer is coming out to be, oh sorry, it will be written as 0.0205 multiplied by 931.5 mega electron volt. For me, it is coming out to be negative mega electron volt. But they are saying it should be about 18. So it could be 18.5 or something. But why is there any some small difference there? I believe they must not be using 1.007. Possibility is that they would be using 1 for the neutron. But let us see what they have done. And we are also getting the answer which is approximately equal to 18. So this is how we do this question. Let us go to the mark scheme. So first of all, the mass defect, this. Okay, this is like not 7, but it is 8. So overall, they are having this. And then uh, this is the mass. And then they just multiply this with the 931.5. And so they're getting 17.512. So I think my calculation was wrong only from this point of view. Like it was 1.007 that I have taken. But anyways, so this value, like the mass of proton and mass of neutron, you must remember. Even I was remembering this thing, but I'm just forgetting it. Like it was 7672, I think. And this was about 0084 something. So I mistakenly took the mass of proton in the place of mass of neutron. So this will be the answer. No problem here. Let us now go for the next question. Estimate the specific energy of hydrogen by finding the energy produced when 0.4 kg of deuterium and 0.6 kg of tritium undergoes fusion. You want to comment on the specific energy of hydrogen. Okay, so specific energy. So this is the reaction that is taking place there. So specific energy, let us first of all understand what is specific energy. It is the energy produced if you are burning 1 kg of the fuel. So in this case, the fuel is hydrogen. So we would be burning 1 kg of hydrogen. So clearly 0.4 kg is deuterium and 0.6 kg is tritium. Now, at this point, students will be confused. Like, what the hell is happening? Why 0.4 is given differently and 0.6 is given differently for tritium? How to engage in this thing now? So, the reaction that is given here, it can be understood in two different manners. Number one, like one atom of deuterium is reacting with one atom of tritium and it is producing one atom of helium, one neutron, and some energy is produced, which is given by 18 mega electron volt. So this can be taken as 18 mega electron volt. And this can be taken as like one atom reaction. But the same reaction can be understood in the terms of moles also. So it's like one here, and one here. So they are all 1 mole. So 1 mole of deuterium reacting with 1 mole of tritium. So initially there are 2 mole of the quantity. 1 mole is deuterium, 1 mole is tritium. They are reacting with each other and they produce 1 mole of helium and they produce 1 mole of neutron. Now, the student, those who don't know what I'm talking about, like how I'm going to write one there, let me give you one example of this kind of nuclear reaction, like uranium 23592. It is getting reacted with this. It produces, there is a reaction in which the barium and krypton is produced. In this reaction, three neutrons are produced. Now this is the integer value, like integer value that is written in front of neutron. Here it is not written, here it is not written, so we can just assume it to be 1. Here it is written 3, but we can just assume it to be 1. Like here it is 1, here it is 3. Now what does it mean? 1 mole of uranium atom, it will react with 1 mole number of neutrons. It will produce 3 mole of neutrons. So this is another way of reading a chemical reaction or a nuclear reaction. Okay, so now coming back to the same question again, this was just the background information. Now, so another point that we need to remember here, now 0.4 kg and 0.6 kg. Let us try to find number of moles of this. So number of mole is given by that mass in gram. So 0.4 into 1000 is the mass in gram, divided by the molar mass, which is 2. So this will become 0.2 and it will become 200. So 200 mole of deuterium is present in the sample which is going to react in the nuclear reaction. 200 moles are there, not 1, not 2, 200 moles. Okay, and what about the tritium? 0.6 into 1000 divided by 3. Again it is giving us the value 0.2. So again we have 200 moles of tritium. It clearly means that number of mole of hydrogen, number of mole of tritium and deuterium, they are same. So our complete fuel is 1 kg inside the nuclear reactor, and at the end of the day, all of it, 100% of deuterium will consume 100% of tritium, and at the end of the reaction you would be having 200 moles of helium and 200 mole of neutrons. Okay, fine. Having said this, now another thing that we want to understand is, like, one atom is producing this much of the energy. Okay, so one atom of deuterium is producing 18 mega electron volt of energy, but 200 moles, it means like you have to multiply by Avogadro number. These many number of atoms of deuterium, when reacting, they will produce 18 mega electron volt multiply by 200 Avogadro's number. This is the total energy that is liberated. Now everything cut short, let me explain you this thing again. In this reaction talks about one atom of deuterium, one atom of tritium, and some energy is produced. So we have to first find how many number of atoms are there in 0.4 kg of hydrogen of deuterium, and then we will say these many atoms will be producing this much of the energy. One atom is producing 18 mega electron volt, two will be producing double of that, three atoms will produce triple of that. So this will be producing multiply by this. So your answer will be 18 mega electron volt will be converted into joule, multiply by 200 moles. 1 mole is having 6.023 10 raised to power 23 number of atoms. This is the total energy that is produced by this reaction if using 0.4 kg. Now 0.4 kg of deuterium, 0.6 kg of this, it means 1 kg of hydrogen. So this much energy is produced by burning 1 kg of hydrogen. So this is what is your answer as specific energy. My dear students, I know, I understand this thing, that this is really a complex question. It's a difficult question indeed, and many students have already asked this question to me, like what is happening in this question. I know this is difficult. Please watch the video again and again to understand what is happening in this. So this is how we do it, and we are not going to calculate anything, but let me show you what they are doing in the mark scheme. Okay, so they have done the same thing. You see, 0.4 kg of deuterium is this. So it's like 0.4 in grams divided by molar mass. This is number of moles, 200. 200 number of moles, multiply by Avogadro number. This is the number of nuclei present in the sample. 0.6 tritium is of the same number. So they are equal to each other, and they are reacting, and they are fusing together. They are creating 200 mole of helium. So the energy produced by one is given. So this is the total energy. This is number of atoms. 17.1 is the energy that was there. 10 raised to power 6 is for mega. This is for the conversion of electron volt into joule. You divide by the total mass of hydrogen, which is 1 kg, and you have the answer, which is this. So they have actually done the same thing, but they have just written it in a shorter manner. So this is how we do this question. The total specific energy. Is there any other easy answer, easy way that we can do? I think they have done it in a easy manner also. Okay, let me see if we can also think an easy manner. So easy thing will be if we can work around in AMU. Yeah, we can think on that. Uh, so we knew the mass defect in this. Uh, yeah. Anyways, don't go for that because I'm getting confused. If you think about that, if you can go, definitely you are welcome to go there. Okay. So this question is done now. Without wasting any time, let us go to see. I think even this question is very, very long. It is hoped that the nuclear fusion will be used for commercial production of energy. Outline two difficulties of energy production by nuclear fusion, one advantage of energy production by nuclear fusion over to nuclear fission. Okay. So the advantage is that in this case, the energy produced is more than the energy produced by that, like the specific energy, I would say. Specific energy of hydrogen is greater than the specific energy of uranium. That is why this is the advantage, and we need not to find what is the specific energy of uranium. Obviously, you can just write it, and this is the advantage. Two difficulties are that fusion undertakes under two conditions. Number one, the density and pressure should be high, and number two, the temperature should also be very high. These are the two conditions which usually do not meet. Like, it's difficult to get both of these conditions, to meet both of these conditions properly. They need high temperature because proton and proton are not ready to react, because they have electrostatic repulsion. So they are not, because of the Coulomb force, they're not able to collide with each other. So they need a sufficiently high temperature so that they just collide with each other. And by the kinetic theory of gases, we know that kinetic energy is directly related with the temperature. So temperature has to be very high. Point number two, hydrogen protons are very small in size, so they are just moving at a very fast speed, but they are not colliding with each other because one proton is not able to find another proton. That is why the pressure has to be high, density has to be high, so high that if they are moving with that kind of a velocity, they will find another proton to collide with, and so that will facilitate our nuclear fusion reaction. So these two conditions are really very difficult to meet, and that is why nuclear fusion reactors are not usually used. Okay, and the point number three is this is uncontrolled reaction. Even that is, you can also write that. So this cannot be controlled, but fission reaction can be controlled by using control rods. But if you are setting this kind of fusion reactor, fusion is not controlled. So this is always uncontrolled. Let us see what they have written now. Yes, so they are saying it requires high temperature, it must overcome the Coulomb force, difficult to control, difficult to produce excess energy, often energy input is greater than the output. Yeah, because when you want to create that kind of a temperature, this statement is very important, I tell you. um, usually what happens is when you do this thing, like you produce those high temperature by using nuclear fission reaction. Like first uranium is undergoing a fission reaction to produce that high temperature, then you use hydrogen as a fuel. So overall, if you see, you have to give in more energy, and the energy which is produced by the hydrogen, it is compensated, so it's not that very useful. But there was a recent news only, I think 2 years back. This is 2024, 23, 22. So I think in 2022 there was this news coming from United States that they have achieved first time the nuclear fusion reaction in the nuclear reactor, in which the net energy produced is more than what the energy given by, like the energy which was given by us. So more energy was produced. It was done first time in United States in some university or some nuclear fusion reactor, I don't remember. The news is from 2022, you can look forward to that. So this refers to that kind of a news. Difficult to capture energy and difficult to maintain constant reaction rate, fine. What is the best part? Plenty fuel supply, so the larger specific energy. So technically specific energy is more. Yeah, no radioactive waste is produced, even that is a very important point. Let us now move to next question and hope that question will be completed soon. But no, it is not in a mood. Okay, let me take a break of 1 minute. Okay, tritium is unstable and decays into the isotope of helium by beta minus decay. So now we are moving into radioactivity. So tritium is converted into an isotope of helium by beta minus decay with a half-life of 12.3 years. State the nucleon number of helium isotope that this decays into. So technically we have to write the complete nuclear reaction, otherwise we will not understand it. So tritium, it is undergoing the radioactivity, so it does not need any facilitating particle like neutron or something that would be colliding with each other, nothing like that. So this is producing beta minus decay. So beta minus is like this. So by using a law which is called Soddy-Fazon law, I told you many times now. So this 3 is equal to 0 plus this. So helium will be produced. This is 3. And atomic number, because it is -1, so atomic number here will be double. So see, 2 minus 1 is equal to 1. 3 plus 0 is equal to 0. So this is a very simple law that we use in chemical reactions in normal chemistry. But this law is even correct and it is applicable on the nuclear reactions also. This is known as Soddy-Fazon law. So Soddy-Fazon law says this thing. So accordingly, we can find this thing. Another point to be noted here, in beta minus decay, always atomic number increases by 1. So here the atomic number is 1, here the atomic number is 2, and the mass number does not change. So state the nucleon number. So this is the nucleon number of the helium isotope. So your answer clearly here is 3, and that's it. So I would be showing you the answer for this, but later, because it has not many things to see. Now we want to show the beta minus decay here in this Feynman diagram. I think the Feynman diagram describing the beta minus decay of this into helium. Yeah. So this, my humble advice to you is that you can even remember the reactions and the Feynman diagrams and each and everything about two reactions. Number 1, beta minus decay. Number 2, beta plus. You can even remember that. So beta minus decay is taking place when neutron is converted into proton. So first of all, let me tell you what is the nuclear reaction that takes place, and you have to remember it. Neutron is converted into proton, and this is -1, 0, and electron is -1. So even this is having a bar on its head. So this is bar, even electron is like negative. So you can say it is a bar here. You can just remember this. Okay, this is just a method of remembering. So this is electron antineutrino with 0 mass and 0 atomic number, or the proton number. Yeah. So Soddy-Fazon rule is completely valid here. 1 is equal to 1 plus 0 plus 0. 0 is equal to 1 minus 1 plus 0. So this is what is happening. So this neutron is going to convert itself into proton, and another particle will be given out, but this mediating particle or exchange particle, so we will be showing this exchange particle like this is negative W in this case. Okay, why negative W? Even this is a logic. There is a conservation of charge principle here. This proton is becoming a positive one. Neutron, before the reaction you have a neutral body here, so after the reaction also, like, it is the negative thing here. Okay, okay, so this is neutral, so this is W minus. We can write this reaction as this, plus W minus with the mass number 0. Yeah, so this is the charge conservation principle. And this particle is also having a age which is like really very small, like 10 raised by negative 18 seconds or something. And after that, it has to break down into two parts. So it will be giving two things. One will be the particle, and another will be the antiparticle, these two things. So electron is released, and this is the particle. That is why the direction shown will be the same as that of this thing. The time is moving in this direction, and there is this antiparticle there, and this direction will be the opposite. um, okay, so sorry for the disturbance. There is my kid backside, but I'm not in a position to close this video because I have already given 25 minutes. So please, I'm sorry for that. But anyways, you can still like concentrate on me. So this is the electron. Now here there is a concept. You see, if electron is a particle, the direction of this will be same as that of the time. Now this is the antiparticle, which is this, and the direction will be in the reverse direction. So this is the Feynman diagram here. And so students, you can even remember this thing now. Just remember it. Another very important point that I can tell you here, which will facilitate you, like, everything is negative in this. Negative is produced, electron is negative, and this is also having a bar on its head. So you can always remember this thing, that whenever beta minus is produced, the exchange particle will be negative. The another particle which is produced is also having a bar on its head. It is antiparticle, and electron is negative. Proton is positive. Got it? Easy method to remember. Okay, so we would be moving to the next question now. Estimate the fraction of tritium remaining after 1 year. Okay. Okay. Estimate the fraction of tritium remaining after 1 year. So for this question, we have to consider the half-life, isn't it? Yeah. So there is the formula. N is equal to n divided by n naught is equal to half raised to power t divided by t half. Again, this is a very useful formula, but this formula is not given in the data booklet or in the books. So you can note down this formula and you can see the application for this formula from this question now. So the half-life for the tritium is given as 12 point something, isn't it? 12.3 years. Yes. So the fraction remaining after 1 year. So n is the number of nuclei remaining. N naught is the total number of nuclei with which you started the reaction. So the fraction is n divided by n naught, which is equal to half raised to power 1 divided by 12.3 years. Now the unit for t as well as t half should be same. It could be seconds, minutes, hours, years. So both should be in the same unit. So this is 1 year and this is 12.3 years. Thereby we can find the fraction that will be remaining after 1 year. So this will be your answer. And how can you find it? Or you can use your calculator. And I am not having the scientific calculator, so I will not be doing it. Let us go to the mark scheme and see if what we have done is correct or not. Okay, so this is it. Yes, you can clearly see W negative is shown, proton is shown. So this is proton, W negative, electron, and antineutrino. Be very careful about the direction that is shown in the Feynman diagram. I have explained these Feynman diagrams in detail in paper 1 questions. So if you have any problem, just go to the playlist 7.3, and you can find all the questions there in complete details there. So the time is this, so you can clearly see these directions. Please mind this thing, that these directions are not the direction of motion in which electron is going or in which antineutrino is going. No, if this direction is same as that of time, we are referring to particle. If the direction is opposite to the direction of time, we are referring to antiparticle. So don't be confused with the direction. Okay, so this is the direction, this direction will be the direction of the time. So if the direction is opposite, we are talking about antiparticle. That's it, nothing more than that. Okay, so having said this, let us go to this thing now. Okay, so they have not used the formula that I have told you. N divided by n naught is equal to half raised to power 1 divided by 12.3. I think if you would be using this formula, even then you would be getting the same answer. But if you do not want to use this, because this formula is not used in IB, like they are not giving it anywhere, neither in the books nor in the data booklet. So probability is that if you would be doing this thing, might be that they may uh, not give you the marks. Possibility is that. You can please talk to your teachers for that sake. No, 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 no. Sorry. Just cut the crap. They have done the same thing. So we can use this formula. Thankfully, this is given here. You can clearly see half raised to power 1 divided by 12.3. It is written here with the ors on both of the sides. So there are other methods also to do it, but the method that I have given to you is perfectly correct, and that is completely usable, although it is not given in the data booklet, although it is not given in the books. Okay, dear students, so this is how we do this question. And that's it. I think this is the last part of the question. Yes, we would be moving to question number 6 later. Okay, so this is it. Again, it has consumed 30 minutes. Oh my God. Okay, then all the best. Bye. See you in the next video. Thanks for joining. Share the video with all your friends. Okay, dear student, let us see what is there in this question. The centers of two identical fixed conducting spheres, each of charge plus q. So this is plus q and this is also plus q. They are separated by a distance capital D. C is the midpoint of the line joining the centers of the sphere. Sketch on the axis how the electric potential V due to the two charges varies with the distance r, small r, from the center of the left charge. Okay, that is x is equal to 0. No numbers are required. Your graph should extend from r is equal to 0 to r is equal to capital D. Okay, so this is the graph in front of you, and it wants you to comment on the potential. Okay, so what is happening? We have to be very careful here. Like at this point, this is like r is equal to the small r is equal to the radius, or you can say capital R, but it is not given, so we can just assume it to be capital R. And we have to be careful for this region also. And this is x is equal to D. This is x is equal to D. So we want to make a graph from x is equal to 0 to x is equal to D. And the graph will be about the potential. So point to be noted here is that the potential is given by a formula that is the potential is given by K capital Q divided by R, where capital Q is the charge of that particle, like which is the source charge, and R, small r, is the distance at which you are trying to find the potential. So this potential is given by this. Now what happens is, let us discuss about the point C, and let us try to find like what will be the potential at point C, and that will clarify each and everything. So this charge is capital Q, and from this point, from the center of the charge, we would be measuring the distance. That will be clearly d by 2, isn't it? So at this distance r, like we can just assume it to be small r, like small r is a random value, so it could have any value, it's a variable, let us say it is small r. So the potential will be given by kq by r. So we will first find the potential due to the first sphere. Let us call this first sphere, I'm just naming it, but it's not like first or second, but just name it. The concept is positive charge will cast positive potential everywhere, like around itself you would be finding positive potential if you're referring to the positive charge. So this is positive charge, so there is a positive potential that is created by the first sphere. The second sphere is also positive charge, so even that is casting positive potential everywhere, so even this is going to create a positive potential at this point. Now, potential is a scalar quantity, although it can have two values, like either positive or negative. Negative charge will be creating negative potential. Positive charge will create positive potential. In this case, both of charges are positive, so V1 and V2 are positive. Now, because it is a scalar quantity, we were just going to add it in a simple algebraic manner, so that will be V1 plus V2. So this will become some potential here. But as you start reducing, like some, it will be added here and you would be having a positive value, let us say. So this is definitely not zero, but it is a positive value here, something. The another concept that you need to understand is, like, as the distance reduces from one sphere, as the distance reduces, the value of potential will increase. If the value of potential will increase, so this potential V1 is increasing but V2 is reducing, but the reduction will not be that big, but the increment will be very high. Okay, so increment will be exponential, so that is why if I'm going to talk about this point, so V1 is going to increase multitude times, but V2 will be decreasing, but it will not be decreasing that much. So I can say that here the potential is at this point, and same symmetry will be there because there is a symmetry in the question, like charges are equal, they are equally spaced and everything, it's completely uniform, both are positive charges. So this will be the V and this will also be V, and in between there will be this kind of, we can say, kind of variation. Now, what about inside of a sphere? So this is the potential, like let us say this is the graph. So this is the potential at the surface of this, and this is the potential at the surface of the conductor. So it is not going to increase. It means that the potential due to, like, whichsoever surface, whatever is the potential here, that potential is going to remain constant now. So this will become like this. So whatever is the potential on the surface, that is going to become constant because there is no electric field inside of a conductor. And there is a, like, it's a big concept. E is equal to negative dV by dr is the formula that relates electric field and the potential. So electric field inside a conductor is always zero, whether the electric field is created by somebody else, some other charge, or it is being created by the charge itself, whatever. The electric field inside a conductor is zero, and that can happen only if the potential difference is zero. So there will be no potential difference here. Similarly, this is going to be a constant value here. So even this is going to be a horizontal line because the potential inside a conductor is always equal to the potential at the surface. Solid sphere, it's in the case of no, sorry, not the solid sphere. This is the case of shell, basically, but electric field on the two charges vary. Yeah, but they are talking about the charges only, so the radius is not given. Yeah, so we can just assume it to be this. A bit confusion is here because the radius of the sphere is not given. But anyways, so this will be um, horizontal. There is no other option. So this is what is going to happen, and the potential will be this. Like, if I assume that this is not a sphere but this is actually a charge, let us say this is a charge, so the radius is the radius is negligible, let us say. So when this r will become zero, the potential will become infinite. So your answer should be at this surface, it should be in an asymptote should be there, it should go like this, and it should go like this. So there will be some asymptotes, but that is not the case in this, because I think they will be taking it as a sphere, and we will see it in the answers also. Okay, so this is how we do the first question. Let us see what is the answer that they have given. And yes, they are talking in the same manner. Constant non-zero within the spheres. So it is a constant value but non-zero value within the sphere. A clear non-zero positive value minimum at C. So C's value is positive, but it is minimum, as we have already told you. Symmetric bowl shape up curved between. So this will be a symmetric bowl. So the symmetry of like this is basically the mirror image of the other. So there is a complete symmetry there. Anyways, so this is the answer for the first question. Let us go for the second one. Calculate the work done to bring a charge Q from infinity to the point C. Now, how are we going to do this? So we are going to use the formula that work done is equal to the product of charge and the potential difference between two positions in which a charge small q is moved. So we have to find the potential at two positions. Number one, infinity, and number two, C, because the charge is moved from infinity to point C. So obviously the potential at infinity is always taken to be zero, whatever it is, like there are two spheres or three spheres, doesn't matter. So the potential at infinity is zero, but the potential at C is not zero, as we have already seen in our graph. So we will first find the value of V1, then we will find V2, and then we will add it. So V1 will be K Q divided by R, which will be half of this, kinda 0.6 meters. Q value capital will be taken, not the small q. Okay, capital Q. The source charge is important here. This is the potential because of the first charge. Now the potential because of the second is also going to be exactly same. So V1 is equal to V2, and now we are going to add them. So our total potential is V1 plus V2, which becomes KQ divided by 0.3, because it is actually multiplied by 2 now, because there are two potentials like V1 and V2. So they are just getting. So this is the net potential at C, isn't it? And the potential at in this is zero. So what is delta V? So now we would be talking in the terms of like final minus initial. So final is VC, initial is zero, which is at infinity. That will be work done. So from by using that formula, W is equal to Q into VC which is this, into capital Q divided by R. So we have just substituted our values here, and now we can solve this. So this and this gets cancelled out, and this decimal can be removed by multiplying 10 in the numerator. So this will be 3. So 4 3s are 12, 12 2s are 24. So 24 into 10 is negative 2. So 0.24 joule. This is the net work done in bringing a charge from infinity to that point. Now the answer will be 0.24. That's it. And let us now move next. So let us see what is the answer. 0.24, clearly the answer that we get is absolutely correct. And let us go for the next part, which is 6b1. Okay, so the small positive charge q is placed at a distance x from the center of C. This is a positive charge q. This is also a positive charge q. But this is a small charge q, but it is also positive. Now this is placed at a distance x away from the charge C, from the point C. The distance x is very small when it compares to capital D. The magnitude of the net force on the charge q is given by this. So this is the net force. So let us see, F is equal to 32k capital Q small q capital D cube into x. This is the force, that is the net force which is acting, and only the magnitude is given. They are still not talking about the direction, but we will make it. Explain why the charge q will execute simple harmonic motion about C. So whenever you get a question like this, like why it is going to be a simple harmonic, The answer is again like always the same. What is that? This F has to be replaced with F is equal to m into A. So mass of the charge, let us say this mass is m. So this mass goes to the other side. So we can say acceleration is equal to x. So acceleration is directly proportional to x. And which direction will it be? Because it has to be negative x, otherwise it is not a simple harmonic motion. So we have to prove it that the direction is towards the mean position. Now obviously this charge is also casting a repulsive force here. It would be creating repulsive force here, but this charge is also creating a repulsive force, but this force will be greater in blue, and it will be greater than the other force. Why? Because the distance from the second charge is lesser, but the distance from the first charge is bigger, so that force will be lesser. So there is a net force which is in the right hand side direction, which is towards the mean position. So definitely there is a negative sign also which is involved here. So we can say that this is the necessary and sufficient condition to prove that the motion will be a simple harmonic motion. So that's it. So this condition is fulfilled, and we can clearly say that yes, this charge will be executing simple harmonic motion. Okay, let us now move to next thing, and I would be showing you the answer later. So the mass of the charge is given now. Calculate the angular frequency from this and this, and the mass is also given. So angular frequency. So we created this thing earlier. So I'm going to continue from this position only. Now, so how to move now? So we know that the fundamental equation of simple harmonic motion is given by acceleration is equal to negative of omega square x. See, my dear students, whenever it is about the simple harmonic motion, you are going to get a repeat telecast of this question again and again. Nothing new about it. The only formula is A is equal to negative omega square x. You just need to follow the pattern. Follow the pattern that I am using here, and it will be good to go with. There was another question I remember doing it like F is given as rho g a x. There was a negative sign. This kind of a question was also there, and in that also you wanted to find the angular frequency, and later you want to find the time period. So you would be following the same pattern in these kind of questions. So this is the pattern that you have to remember. First of all, we will create this expression for acceleration, and then this is the fundamental equation. We are now going to compare it. So omega square will be equal to 32k capital Q small q d cube m. This is equal to omega square, and because you want to find the angular frequency, you have to take the square root. So this is your answer. This becomes the omega, the angular frequency. If you want, like, there are two relations you have to remember. It is like 2 pi divided by t if you want to find the time period, and 1 by t is the frequency f, which is in the hertz. So if you know the omega, you can find the time period for the oscillation, and also you can find the frequency of the motion of the charged particle. Accordingly, you can find like whether you what are they asking you in the question, whether they're asking capital T or the F. So this is what you have to do. So this is the omega, time period, and frequency. Let us see what is the answer given. Calculate the angular frequency. Okay, so we will not be calculating. I will be showing you the marking scheme now. Clearly, they have done the same thing. You see, omega is equal to 32k q divided by md cube square root, and I told you to do the same thing. So omega is there, and what else were you supposed to find? Just a moment. Calculate the angular frequency and the expression in B1. Expression using the data in A2 and the expression in B1. Okay, so basically you want to find the angular frequency, so that we have already done. This is omega 32k capital Q small q divided by md cube. This is what you were supposed to do, and this is the answer that you should be getting, 7.3. So you people can just take your calculators and you can do the calculation that I had just written here, isn't it? Like this. Okay, let us now move next. Yes, the charges capital Q are replaced by the neutral masses capital M, and the charge small m is replaced by a neutral mass M. So this is capital M, this is also capital M, and they are neutral. There is no electrostatic force, and there is this mass which is small m. It is displaced from the point C, so it is taken to the new position now by the distance x and released. Discuss whether the motion of m will be same as that of the charge q or not. So let us see, like they are asking whether this will be making the simple harmonic motion this time also or not. Let us see. So if you take this as the uh, position C, yeah, like this, so this point will be there. So when the mass is here, so we can clearly see that this mass will be applying a force of attraction to this, and that will be bigger because the distance is lesser. Well, this capital M will also be applying an attractive force on the small m, but that will be lesser in magnitude because the distance is bigger. It means that the net force on the mass small m is towards the right hand side, which is away from the mean position, which only means that this is not going to be simple harmonic motion. The only thing is this m is experiencing a mass towards capital M, and someday this mass will go and it will fall onto the surface of the that planet or something. So this is going to happen, but it will not be simple harmonic motion. So your answer is this, that it is not going to be the same as that of the small q. Let us see what is the answer given. Yes, the net force will no longer be restoring and directed towards the equilibrium position, and that is why no motion, it will no longer be simple harmonic motion. Yeah, the motion will not be the same. Okay, dear students, so I think this is the last part. Yes, this is the last part for this question, and this is how we do this question. And so if there is any other doubt, you can also mention that in the comment section. Please share the video with all your friends, tell them to join the YouTube channel, and thanks for joining this YouTube channel, and I would be uploading more questions now. Okay, then this is it. All the best. Bye. Oh. Okay, dear student, let us see what is there in this question. A vertical rectangular loop of conducting wire is dropped in a region of horizontal magnetic field. The diagram shows the loop as it leaves the region of the magnetic field. Explained by the reference of Faraday law of electromagnetic induction, why there is an electromotive force induced in the loop as it leaves the region of magnetic field. Yeah, so with reference to the Faraday's laws of electromagnetic induction, it's uh, quite straightforward that the EMF induced is equal to the negative of the rate of change of flux. So on an average, we can say that it is equal to delta phi divided by delta t. So whenever there is a change in flux associated with a conducting loop, there will be an EMF that will be induced. So it will be acting as if the loop is connected with the battery. And obviously there will be the resistance R and the current will be set into the circuit. So induced current will come into existence. So so this is it. And how can we explain it? So we will say that as it is moving downward with some velocity, so we can clearly say that the area is changing. You can also explain it that the flux is the product of magnetic field within the loop and the area of the loop in which the magnetic field is existing. Okay, so that is the flux. And we can say that because clearly there is a change in area, there is a change in flux. And because there is a rate of change of flux, that will be giving rise to the electromagnetic force, that is EMF. Let us see what is written in mark scheme. The induced EMF is equal to the rate of change of magnetic flux linkage linked with the loop. Magnetic flux linked with the loop. There were some students, those who were asking, like, what do you mean by that? Like, linked with the loop. So the loop is moving through the magnetic field. So there is a magnetic flux which is associated with that loop, isn't it? Uh, Associated mean like what is the flux which is going through it? That flux. So flux is changing because the area enclosed by magnetic field is decreasing. So flux is changing because loop is moving out of the magnetic field, and the rate of change of flux is equal to the EMF by the Faraday's law. So accordingly, we can say that in this case, definitely EMF will be generated. So this is done. Let us now move to next question. Now something data is there. Just before the loop is about to completely exit the region of magnetic field, the loop moves with a constant terminal velocity v. It means that although the loop is having a mass m, it is being acted upon by gravity. So it should be actually falling within the acceleration due to gravity. But instead of having an acceleration due to gravity, it is moving with the terminal velocity. It means it is moving with the constant velocity instead, because there will be some kind of equal and opposite force to the weight. So we can say that now the net force is equal to zero. That kind of equation, that kind of situation can be created. So let us see now. The mass of the loop is given to find the downward weight, like m into g. Resistance of the loop is given. Width of the loop is given if you want to find something. Magnetic flux density, that is the magnetic field strength, is also given to us. Okay, so determine in meter per second the terminal speed v. So in this question, like, let me draw the loop here. Let us say this is the loop, and there is a magnetic field inside. Okay, so the mass is given, so there is a downward force which is weight. And first of all, let us assume that might be like it is moving with the velocity v, and we are also assuming that fine, it is terminal velocity, so the velocity is constant. So if the velocity is v, the magnetic field here inside is b, and the width of this is L, which is given here, width of the loop, and the magnetic field B is also given, V is there. So the EMF induced in this will be given by BLV. This is the formula for the motional EMF. You must be remembering it, BLV. If this is the EMF, kind of we can now assume that this is now having a battery which is associated like this. Okay, but this is kind of imaginative. So there is no actual battery, but yes, there is an EMF induced which would be acting as if there is a battery. So we can find the induced current now. So that will be E divided by the resistance R. V is equal to IR by using Ohm's law. So the current will be BLV divided by R. This will be the current. Now, if this is the current, so there will be like this is a current carrying conductor, and what will be the direction now? So this is the magnetic field, this is the velocity. So positive charge will be going in this way. So this end is positive, so battery will be induced like this. This is positive, this is negative. I always use right hand palm rule that I have been explaining you all in the paper one questions for the topic 5.4. And also, like, I've given a completely different video also, how to find the direction of the induced EMF and all that. Induced EMF is in topic 11.1, I think. No, 11.3. Yes. But anyways, so this is here. So this is the EMI, the current. So it will be like there is a current now that is set here. The current is moving in the right direction. So where will be the force now? Magnetic field is this, current is this, so there will be an upward force. And so the upward force is like this. So I am not explaining the direction rules here because that would be consuming a lot of time. And also I have already done it. So this is the magnetic force, and magnetic force is given by BIL. So we would be using this formula now. So BIL So it is B square L square V divided by R. So this is the upward magnetic force which is acting on the loop now. The other part is already, this part is already out of the loop, so out of the magnetic field area. So we are not concerned with this. We are only concerned with this side. And this side vertical, they will not be experiencing any force because they are actually not cutting any magnetic field line. So only this part would be experiencing a force, and that even in upward direction. So the force in the upward direction is given by B square L square V by R. Although I remember this formula, and the students, those who are like, I'm teaching them in here in India, according to the Indian education system, they are supposed to remember this formula, by the way. So if you want to remember it, you can. If you do not want to remember it, you have to follow this protocol each and every time. So this is the upward force, B square L square V by R. This will be equal to the weight. That's it. So let me create an equation now. Yeah, so B square L square V divided by R is equal to weight, which is m into g. So the mass is given 4 grams. Accordingly, you will substitute all the values and you can find the value of V. This is one and the only method here. Don't think that there will be something else. Like the resistance of the loop is also given. B is given, L is given, V is not given, M is also given. So all the variables are given. Just plug in the value and get the answer. Okay, so let us now move to the mark scheme and see if they have done the same thing. Yes, they have done the same thing. Mg is the weight downwards, BIL is the force which is in the upward direction, and the current is 0.3. So we would be substituting these values here, and from there we can find the value of V. This is the formula that we are already using. B square L square V by R is equal to M into G. So V is equal to mgr divided by B square L square. So this is exactly the same thing that we have done. So this is how we do it. And yes, this question is done. Now let us move to 7C. Yeah, so this is about the capacitors now. Capacitors is 11.3. Yeah, 3 capacitors. C1 is 3 microfarad, C2 is 2 microfarad, and C3 is 4 microfarad. They are connected to a cell of EMF 12 volt, negligible internal resistance. The capacitors are initially uncharged. The total capacitance of the circuit is. So first of all, we have to apply the principles of series and parallel combination to find what is the total capacitance of this system. That should be easy for majority of students, but anyways, I would be doing this. So these two capacitors, first of all, they are in parallel to each other. So we know that when the capacitors are in parallel, C total is taken as C1 plus C2. It is the opposite case of the resistance. In resistance, this was done in series, but in capacitors, it is done for the parallel. So 2 plus 4 will be 6. So another circuit can be drawn here. This is 6 microfarad and this is 3 microfarad. Now they are in series. So we would be using the formula for series. So 1 by Ct is equal to 1 by C1 plus 1 by C2. But this formula is quite difficult to apply. It needs a bit of more mathematics, but there is a simpler version. If you create this version, you would be able to do the calculation even in your mind. Like, this is just nothing. Like, I have just taken the LCM of this and then I have reciprocal it. So this is actually the same formula. The only thing is that the formation is different, which is quicker as per the calculation is concerned. For example, 3 and 6, just apply. 6 3s are 18, 6 plus 3 9. Clearly the answer is 2 microfarad and we have done it. So this becomes 2 microfarad. So your answer is 2 microfarad here. Otherwise, you can just see this thing. First of all, this parallel combination is converted into series. Like, these two have been converted into 6. And then this has been using the formula for the series. We have found that the answer is 2 microfarad. Let us see what is the answer given. Yes, the answer is 2 microfarad. And let us go for the next question now. The total energy stored in the 3 capacitors. So we want to find the total energy. So it will be half Ct V squared. So the total capacitor is 2 microfarad into the potential. I think it was 12. Yes. So it is just this half this. So 2 and 2 gets cancelled out. It will be 144 microjoule. Now this is the total energy which has been stored in all of the three capacitors somewhere. Some energy is in C1, some is in C2, but the total is 144 microjoule. Let us see what is the answer. And yes, it is 144 micro. I just took it as 10 raised to power negative 6, but they have created 10 to power negative 4. That is why the answer is 1.44, but otherwise the answer is typically the same. Let us go for the third point now. The charge on C2. Okay, I think that should be the last part. The charge on C2. So we want to find the charge on C2 now. Okay, so well, this is one of the kind of hard question, I would say, because in this, like, we have to follow the complete process. There is no shortcut. So we have to go for the complete process. And what is that? The step number one is that we must know what is the total C equivalent or C total. That we already know, by the way, now, which is 2 microfarad. So our system reduces to only this. From this system, we will find what is the total charge that is on this total capacitor. So Q is equal to CV. So 2 micro multiplied by 12. So it becomes 24 microcoulomb. So 24 microcoulomb is actually the total charge on, like, that is, I will not say that this is the total charge which is on the capacitors, but this is the total charge which is given out by the battery. This is bit I would say confusing. I will show you why. So the total charge which is coming from the battery is 24 microcoulomb. This we have found here. So this is the charge which is coming from here. Now the principle of series combination. Now what was the series combination? This and this. I remember this was 6 microfarad and this is 3 microfarad. This was the intermediate circuit that we have drawn earlier. Just try to understand. This is 12 volts. So 24 microcoulomb charge has been withdrawn from the battery. The same charge will go to both of the capacitors. This capacitor will be having 24 microcoulomb separately. This charge, this capacitor will also be having 24 microcoulomb as a separate charge. Now, many students will be confused that the charge withdrawn from the battery is 24 microcoulomb, but the total charge here seems to be 48, isn't it? But no, dear students, it is not 48. Try to understand. This part is not even connected. You know what is happening? Induction is happening here. So let me try to explain you if you are able to understand. So this plate becomes positively charged, but this plate is actually not connected, isn't it? The negative plate is not connected here. It is induced. So negative charge on this plate is induced, which in turn is inducing this positive charge on the other plate of the other capacitor. So this positive charge is inducing negative charge on the second plate of 6 microfarad. Because they all are metallic plates, so the induction is exactly same. So this is also 24 microcoulomb. This is also 24 microcoulomb. Okay, so point number one is done, that this is definitely 24 microcoulomb. C2 and C3 are not equal to each other now. Even that is a problem. If it would be equal, we would have said that, okay, fine, these two are equal, so the charge will be equally distributed. But now the charge is not equally distributed. Now there is another problem. So what can we do now? So 24 microcoulomb is this. We want to have the charge on C2. Now there is only one formula, which is Q is equal to CV, and in this case C is known, V is not known, Q is not known, so we have to find the potential V. So there are two methods now. The charge on this is known, 24 microcoulomb, and the capacitance is also known. So we can find the potential V1 across this. So V1 according to this formula is given by Q by C. So 24 micro divided by 3 micro. So it is 8. So 8 volt out of 12 total volt, 8 volt is taken up by this capacitor. So the remaining 4 volt exist across this. So 4 volt is the potential difference across C2. 4 volt is the potential difference across C3. 4 volt. Now we can find the charge, isn't it? So Q2 will be equal to C2 V2, and pardon my space management, that has been really weird in this question. So 2 microfarad is the capacitance, and V2 is 4 volt. So 4 2s are 8. Micro has to be there, coulomb. So the answer for this is 8 microcoulomb. As I have already told you that this kind of question is like longest of all, and there is no shortcut, and obviously there are many places where there is a high chance that you would be committing some or the other mathematical mistakes. So you have to be very careful throughout the question. So your answer in this question will be 8 microcoulomb. Well, if I have not committed any mathematical mistake, we will see whether the answer is 8 microcoulomb or not. And yes, the answer is 8 microcoulomb. 8 microcoulomb. And so they have given a couple of methods here. The charge on C1 is CTVT. The voltage is found to be 8, and then the voltage is found to be 4. This is what we did actually. So the voltage across C2 is half that across C1. Okay, so this is kind of not a very good method. C3 is equal to twice of this, leading to this. Anyways, so this method is the best method that we have employed. Easy, you can follow step by step protocol to reach the answer, and the answer is 8 microcoulomb. Okay, dear students, I think this is the end of the question. Yeah, the next question is question 8 now. So this question is now completely done, and this is how we do this question. So if there is any other doubt, you can please mention that in the comment section. So after this, we would be moving to the next question. No worries at all. Please share the video with all your friends, and thanks for joining the YouTube channel. All the best. Bye. Okay, dear student, let us see what is there in this question. Photons of wavelength 468 nanometer are incident on a metallic surface. The maximum kinetic energy of the emitted electron is 1.8 electron volt. Calculate the work function of the surface in EV. So we have to find the work function. This question is from the photoelectric effect, which is which topic? I believe topic 12, I think. I'm not sure about it, but anyways, okay, no problem. So this is the metallic surface, and this is photosensitive metallic surface. So when the energy is coming onto this surface, like they are closed in a conduit, you can say, or something like that. So this is another cathode, and so they need not to be having any battery, by the way. So they can be connected without anything, like there is only ammeter here, and they are connecting this thing like this. So when the light is exposed, like this surface is exposed to the light, and light is illuminating the surface, what happens is that it is getting electrons out. So electrons jump out of it, and they start moving, like they have certain kinetic energy, so they keep on moving towards the other plate, and that is why the current is there, and the current is not zero even without the battery. Now the wavelength of the photons, the incoming photon, is given as this. So we know that the Einstein equation is given by hc by lambda, which is the energy of the incoming photon, which is actually absorbed by the electron now. So this is converted into two things. Number one is the work function. Work function is defined as, like, you can call it W0, or in many books it is written as phi 0, like whatever thing, like symbol that you can use. Work function is defined as the minimum amount of energy that has to be given to the electron so that electron jumps out of the metallic surface. So this is defined as minimum energy. So this is the minimum energy plus the rest of the energy will be obviously the maximum kinetic energy. So work function, like there will be some electrons, those who would be only at the surface of the metal surface, so the work function will be very less, and that electron will be having the maximum of the kinetic energy. There is a chance that there will be electron which are like embedded in between, like with well deep within the surface, and so work function becomes very high. Obviously the leftover energy is very less, and that is why the kinetic energy gained will be smaller in those cases. So some electrons will be having more kinetic energy, some electron will be having lesser kinetic energy. There was this question also, I think, in paper one sometime, and the question was, do all the photoelectrons which are coming out of the metal surface, they have the same kinetic energy? So clearly the answer is no, they do not. Some electrons are moving at a faster speed and some electrons are moving slowly. Okay, so this is the equation that we are going to use now. The wavelength is given as 460 nanometer. We can just plug in our values here. Negative 34. C is this, and the wavelength is 468 nanometer. This is hc by lambda, that is energy of the photon. Negative the maximum kinetic energy. So maximum kinetic energy is in ev, and you want the answer in ev, so it will be better if we convert hc by lambda, which presently is in the unit joule. We have to convert it into electron volt. How? By dividing it by the charge on an electron. So this is the conversion factor, I will say, and this is how you convert joule into electron volt. You divide the energy by the charge of the electron, and so whatever is the new numeric value, that will be energy in electron volt. So this is energy in electron volt. When we solve this, we subtract from like 1.8 from this, so you would be getting the work function. So I am not doing anything here, we will not be calculating it, so we will directly move to the mark scheme and we will see if they have done the same thing. Okay, yes, so this is the mark scheme in front of you. Emax is given as hc by lambda minus work function. As I've already told you, I wrote it as W, they are writing it as phi. So this, and so phi is equal to hc by lambda minus Emax, one is the same thing. So this is hc lambda, and this is to convert joule into electron volt, and we would be subtracting 1.8 out of it, so you are getting 0.86 electron volt. Always remember that when we would be making calculation, we can calculate it in any decimal, but at the end of the day, when you have to report the answer, your final answer should be having two significant figures. So the two significant figure is 0.86. So this electron volt will be the work function for that metal surface. Okay, let us now move next. Remember that this value is 0.86 ev. 0.86 ev. Yeah, now let us go for the next. The longest wavelength of the photon that will eject an electron from the surface. So coming back to the Einstein equation, hc by lambda is equal to work function, and the rest of this will be given out as the kinetic energy. But as I've told you that this, when you use Ke max, you are basically talking about a particular electron for which the work function was minimum. But there is a possibility that the work function is different, like some kinetic energy is not this, and there are a couple of other things also. But in this case, what we do, we are going to mess up with the wavelength of the photon. So there is a minimum wavelength which is known as threshold frequency or threshold wavelength. Lower to that, like from frequency point of view, lower to the frequency, from wavelength point of view, you cannot have more wavelength. So this is the maximum value of the wavelength that you can choose if you want to get an electron out. So the longest wavelength will be, like you see, the energy of a photon is hc by lambda. Now longest wavelength means lesser energy, so minimum energy to get an electron out of the metal surface. So that can happen if we are taking this kinetic energy to be zero. Let us say that all of the energy of the photon, like it is not that enough, but only that the electron is able to get out of the metal surface, and it will be having zero kinetic energy once it's get out of it. So this will be related with zero. So work function is equal to hc by lambda, and we want to find the wavelength. So this wavelength will be the maximum possible wavelength, or c by lambda is the minimum frequency. So both you can find threshold frequency or threshold wavelength. So this will be the equation. Again, I am not uh, calculating it, like work function is 0.86. Accordingly, plug in the value, get the answer. So sorry, yes, hc by lambda is equal to work function. So kinetic energy in this equation is taken to be zero, as I've already told you, and you divide it by the charge of electron, and so you create this into ev, because this is ev, so you have to convert it into joule, because here for the wavelength you want the answer in SI unit. So EV has to be converted into joule. Okay, so even this is done, even this is done. I don't think that there will be any problem here. Let us go to the next question now, 8b1. In an experiment, the alpha particles of initial kinetic energy 5.9 mega electron volt are directed at a stationary nuclei of lead, which is having mass number 207 and the proton number as 82. Show that the distance of the closest approach is about this. So we want to find the closest approach. Now, this is a different topic. Like again, it is topic 12, the Rutherford experiment that we did, and in that we learn about the closest distance of closest approach. So the earlier question, that is 8a, was about photoelectric emissions, and this is about the Rutherford Geiger Madsen experiment, in which like they were using the gold film and they were bombarding the gold film with alpha particles. This is what is happening here. Now, what is the distance of closest approach? So how do we define it? Let us first understand. Let us say this is the nucleus, and there is a alpha particle here, so it's really far away. That is why I have drawn it in a very weird manner, like alpha is on the other end. So this alpha is having some kinetic energy. So what is the potential energy of the alpha? The potential energy of this alpha will be taken to be zero. Why? Because it is really at far away distance, like kind of infinite. So if it is at infinity distance and we say that there is no interaction present between the alpha particle and the nucleus as of now, so the potential energy will be taken as zero. Now they are coming together. So the charge on alpha is plus 2e. Why? So many students would be having a problem, like what is alpha? Alpha is the helium nucleus. So we can say the atomic mass number was 4 and the atomic number is 2. It means like there are 2 protons and 2 neutrons. Obviously the helium will be having 2 electrons also, but we have to remove 2 electrons. So you remove 2 electrons, so you are left only and only with the nucleus of helium, and the nucleus of helium is containing 2 protons and 2 neutrons. So these 2 protons and 2 neutrons are there, and this alpha is coming. This is called alpha, or you can call it helium nucleus. So this is having a charge of 2 plus, it is coming towards this. It is having only and only kinetic energy and potential energy 0. Let us say it is directed directly towards the nucleus. It is going to hit head on, like from on the central line. Obviously, this is also positively charged, and Z is the proton number. So I can say that Ze is the charge of the nucleus. Like you're talking about gold, you're talking about lead. So in the case of lead, it is 82. It means that the nucleus is the house for 82 protons. One proton is having charge of E. So the charge here will be 82E. Instead of Ze, we can write it as 82E, because this is the nucleus of lead. Now it is coming together, and after some time, like this is the closest of all the distances that it is able to go, the nearest distance towards the nucleus, and at this point it loses all of its energy. It stops here, so the final velocity becomes 0, which clearly means that at this point the kinetic energy becomes 0. Now, if kinetic energy is zero, so where is that energy gone? That energy has converted itself into the potential energy. So kinetic energy is equal to potential energy, and this distance is small r. So when the alpha reach at this point, it will be plus 2e. So all of the energy will be in potential energy. Earlier, all of the energy was kinetic energy. So clearly, we can create a mathematical equation here. Kinetic energy is equal to the potential energy of the system afterwards, which will be equal to from the concept of electrostatic, topic 5, or you can call it topic 10 because we're talking about potential energy. This capital Q into small q divided by r, where r is the distance of closest approach, obviously, because that is the minimum distance. This is the potential energy. This will be equated with ek, that is kinetic energy. Now kinetic energy is given as 5.9 10 raised to power 6 ev. So ev has to be converted into joule. Okay, so because on the left hand side you have the energy and the unit is electron volt, on the right hand side you have the potential energy and the unit is joule. So either you divide joule by the charge on electron, or you multiply the kinetic energy with the charge of electron. Anyways, one is the same thing because we want to have same unit on both sides. So this, and k value is 9 into 10 raised to power 9. Capital Q value is 82e, and small q is 2e divided by r. So this 1e and 1e can be cancelled. So accordingly, we can find the value of r from this expression. Again, we are not going to do anything as of now. You can use the calculator and you can see that yes, you are getting the answer indeed, which is similar to 4 into 10 raised to power negative 14. But let us go to the mark scheme and see what is written there. Now here the charge is 2e, then the other charge is 82e. So the distance of closest approach is k capital Q small q divided by the kinetic energy, which is given as 5.9 mega electron volt. So they have done exactly the same thing that I had written, and you can now just take up your calculators and you can calculate that value that I have given you. So the value is coming out to be equal to 4 into 10 power negative 14 meters. So this is how we do this question. So 8b1 is also done. Let us now move to 8b2 and see what is the next question. I tried to explain you the complete concept of the distance of closest approach. So I think that should be justice that we have done here. But let us say any comments that you have, please do mention that in the comment section. No problem. The radius of nucleus is this. Now, the radius of the nucleus is found to be 7.1 10 raised to power negative 15 meters. Suggest why there will be no deviations from the Rutherford scattering experiment in B1. There will be no deviations like the experiment that we have done now. So that will be showing you the results similar to the results that we predict with the help of Rutherford scattering experiment. So there will be no deviation in our experiment and the experiment done by Rutherford at that time. So why do you think that we would be finding the similar results? Why will we find that kind of thing is, you see that in the other question we found the distance of closest approach, and the distance of closest approach is found to be 4.0 into 10 raised to power negative 14 meter. This is the distance of the closest approach. Now Rutherford said that yes, it will be happening like this only. There will be a distance of closest approach which will definitely be more than the radius of the nucleus, because these two nucleuses are actually not going to hit each other. They are not going to come near to each other within the range of a nuclear distance, we cannot say. So there will be a big gap, and definitely there is kind of 10, the factor of 10 is there, which separates it. It means like the distance of closest approach is 10 times bigger than the radius of the nucleus. So this is r, and so 10 times away is the alpha particle that is coming, and it was stopped at this distance. So it is 10 times the radius of the nucleus. So it's very, very far away. So it is not able to bridge the distance with this much of the kinetic energy. The distance is still big. It is not in the nuclear range of Fermi meters, and that is why there will be no deviation from the Rutherford experiment. Because if the distance becomes very small, then nuclear forces also starts acting. As of now, the alpha particle is far enough, and so the nuclear forces will not be having any influence on the alpha particle. What is that distance up to which the nuclear forces show an influence? That is nearly 2 to 3 Fermi meter, that is 10 raised by negative 15 meters. This is the distance that the alpha particle needs to come into, but it is very, very far away, like it is multiplied by 10. So kind of it's like 10 times this distance. That is why there will be no deviation. But anyways, let's see how they have explained this thing. So the closest approach is significantly larger than the radius of the nucleus, and it is far away from the nucleus. Therefore, strong nuclear force will not act on the alpha particle, absolutely as what I have said. You can refer to the book like Soko's, and there is a graph given there, and they show you that this was what was expected in the Rutherford's theory because of the mathematical expressions that we have. But after it reaches some distance within the nuclear range, immediately there is a deviation from what is expected from Rutherford's theory, thereby proving that nuclear force exists, isn't it? So this is it, my dear students. So this is how this question is done. So this was the last question for this paper 2, May 2023, time zone 1 HL. I hope all of the questions will be very clear to you now, and if there is any other problem, you people can message me on WhatsApp, or you people can message me in the comment section. No problem about that. Okay, dear students, after this we would be moving to some other question. All the best. Bye. What is there in this question now? A ball of mass 0.8 kg is attached to a string. So the mass of this ball is given. The distance to the center of the mass of the ball from the point of the support is 95 centimeters. The ball is released from rest when the string is horizontal. When the string becomes vertical, the ball collides with the block of mass 2.4 kg that is at rest on the horizontal surface. Okay, fine, no problem. Just before the collision of the ball with the block, draw the free body diagram for the ball. Okay, so what is the free body diagram for the ball? First of all, we have to see, and what are the forces we have to see. So the first force that will be there is obviously the weight, isn't it? So weight will be there. You can't get rid of it. Weight will be there. What else do you think is there? Tension? Yes, the tension in the string is this. Now, the tension in the string is also acting like the centripetal force, because of which it is moving in a circular motion. So, because there is no upward and downward force, no, but there will be bigger force here. So, tension will be more than weight. Sorry. So, tension will be bigger because it